Okay, is Wei Yi on?
Yeah, yes, yes, I'm here.
Hi. Wei Yi, would you, I think the easiest thing is if you just
Oh, okay.
share your presentation. Do you have permission to share?
Yeah.
Okay.
Mm, okay.
You want to put it in, there, great. All right, well, let's get the session going. Um,
Okay.
Go ahead.
Okay. Hello everyone. This talk is about fast response of Ethereum precipitation to local and remote emission reductions during COVID-19. So in 2020, the emissions of aerosol and precursor gas were reduced over different regions and countries from February to June due to COVID-19 pandemic lockdown. As shown in this figure, where different colors represent aerosol and precursor gas, the emissions were reduced in February over China, and then the emissions over the rest of the world were reduced in April. So after the outbreak of the COVID-19 pandemic, anomalous increase in precipitation over the Yangtze River Basin has been observed during summer in 2020. So the emissions reductions during COVID-19 um, provides an opportunity to investigate the impact of emission reductions on climate change. Previous studies have shown that the local and the remote emission reductions have different influence on the response of precipitation to local aerosol forcing. And the response of precipitation can be split into two parts. A fast atmospheric response on the time scale from days to months, and a slow response on the time scale of years mediated by sea surface temperature. So in this study, we focus on the fast response of precipitation over the Yangtze River Basin to emission reductions over China and the rest of the world in summer 2020. The CESM tool is used in the study. The atmospheric component is coupled with complex chemistry and forced by observed SST from 2015 to 2020 at 1 degree horizontal resolution. Each case includes 10 ensemble members, and the average is analyzed to reduce the impact of the internal variability. To examine the impact of COVID-19 induced emission reductions, we designed two emission scenarios in 2020. The reduced emission scenarios following Foster et al. And Zheng et al. Are named COVID, while the pseudo emission without COVID-19 in 2020 are named actual based on SSP 245. So we first perform simulations for 5 years from 2015 to 2019, and then branch four runs with different emission scenarios over China and over the rest of the world. In the second and third case, the COVID and the actual emissions are used all over the world respectively. And the difference between these two cases represents the impact of global emission reductions. In the case no COVID saying, the local emissions over China used the actual emissions, while the remote emissions over the rest of the world used the COVID use the COVID emission. The difference between COVID and the no COVID CN case represent the impact of emission reductions over China. In no COVID RW case, the local emission over China is the COVID emission, while the remote emissions over the rest of the world is the actual emission. The difference between COVID and no COVID RW case represent the impact of emission reductions over the rest of the world. To access the model performance in simulating precipitation, we first evaluate the simulated precipitation in June 2020 and changes in precipitation relative to the previous 5 years mean. So the results show that the spatial pattern of precipitation is consistent with the observations. And the drawbacks for the precipitation in June 2020, drawbacks over the YRB and the southern China occurs. For the precipitation anomalies, the model is able to capture the significant increase in precipitation over the Yangtze River Basin. So overall, the model is able to simulate the process associated with the precipitation. And therefore, we further examine the fast response of precipitation to emission reductions over different regions. This panel shows the fast precipitation response to emission reductions in June. The column from left to right shows the changes in total convective and large-scale precipitation. The growth from top to the bottom show the impact from emission reductions over China, the rest of the world, and global emission reductions. The red rectangle represents the area of Yangtze River Basin, and black dots show the significant changes in precipitation. So among the 3 different emission reductions, the local emission reductions over China lead to stronger convective precipitation over the Yangtze River Basin, while the remote emission reductions outside China lead to stronger large-scale precipitation over the Yangtze River Basin. We next investigate the physical mechanism of fast precipitation response to emission reductions. This panel shows the changes in aerosol optical depths and dust optical depths respectively, and the rows from top to the bottom represent the impact of local, remote, and global emission reductions. So over northern and southern China, the LOD decreased, while the DOD changes are relatively small, indicating that the decrease in LOD is mainly associated with reduced anthropogenic aerosol. The changes in aerosol properties further affect low cloud fraction, we're showing this panel. The figure from left to the right show the changes in low cloud fraction due to emission reductions over China, the rest of the world, and global emission reductions. So over northern China, the low cloud fraction decreased, which is mainly caused by emission reductions outside China. Over southern China, the low cloud fraction increase, which is associated with enhanced vertical motion and the atmospheric stability. The next panel shows the changes in downward net solar radiation flux at the surface. The red color represents positive changes, and the blue color represents negative changes. So over northern China, the net solar radiation at the surface increased due to reduced aerosol and low cloud fraction, which is mainly caused by emission reductions outside China. Over southern China, the night solar radiation at the surface decreased due to the increased low cloud fraction. The changes in surface radiation further affect atmospheric temperature, as shown in this panel. This figure shows the pressure latitude changes cross-section of changes in atmospheric temperature over the east area. The red color represents warming and blue color represents cooling. So the atmospheric cooling over the sea and the warming over the land increase the land-sea thermal contrast, which favors the moisture transport from south to north. The panel at top and the bottom show the changes in condensational heating and vertical motion over the east area. Over the Yangtze River Basin, the diabatic heating is enhanced due to condensation, and the ascending motion becomes stronger over the Yangtze River Basin, which is conducive to increasing precipitation. Under different emission reduction scenarios, the local emission reductions over China cause the strongest ascending motion around 30° north over the Yangtze River Basin. The next panel shows the changes in moisture transport and convergence due to emission reductions over China, the rest of the world, and global emission reductions. The vectors represent the changes in column integrates moisture transport, and the red color represents enhanced moisture convergence, and the blue color represents moisture divergence. So the results show that over the Yangtze River Basin, the moisture transport and convergence are both enhanced, which favors the increase in precipitation. For the different emission reduction scenarios, the local reduced emissions over China enhance the moisture transport from the Arabian Sea to the Yangtze River Basin, while the remote reduced emissions outside China enhance moisture transport from the Bay of Bengal to the Yangtze River Basin. So the main conclusions are listed below. Among different emission scenarios, the local reduced emissions over China lead to stronger convective precipitation over the Yangtze River Basin, while remote emission reductions outside China cause stronger large-scale precipitation over the Yangtze River Basin. The OD and low cloud fraction decrease over northern China due to emission reductions, enhancing solar radiation at surface and the land-sea thermal contrast. The vertical motion and the moisture convergence are enhanced over the YRB, leading to increase in precipitation. The local and the remote emission reductions lead to different anomalous ascending motion and moisture transport to the Yangtze River Basin. The implication of this study is that the nonlinearity in the response to earthforcing from local and remote regions requires international collaboration across countries when addressing the regional impact of climate change. So that's all. Thanks.
Well, thank you, Wei. I think since we got a late start, we'll go ahead and move on. Thank you for the presentation. Our next presenter is Xiaohong Liu, who I assume is presenting remotely. Great.
So, can you see my screen? No.
We see your screen. There we go.
Can you see my screen?
Yeah, that looks good. Your screen, and it's in full screen mode.
Is that the full screen? Oh.
Yes.
Okay, thank you. And so I'm going to talk about quantifying the emission and related forcing of unsubordinated dust. And firstly, I want to acknowledge my collaborators, particularly my graduate student, Yang Xi, and she is now at MIT and did most of the work. And we know that dust is the most abundant aerosol in the atmosphere. So this figure showing the red is showing the dust, and it's global transport and emitted from the dust emitted from the North Africa and the Middle East and Asia, and the dust is generally regarded as a natural aerosol, and there's natural dust or ND, and therefore the IPCC do not include the dust when estimating the aerosol effective related forcing like aerosol cloud and aerosol release interactions. And however, there are studies showing that from pre-industrial and to the present day, 1850 to 2000, the dust burden has been based on increased from pre-industrial to present day based on the reconstructed dust the burden, and this is showing the black curve, and the dust has been increased from pre-industrial to present day by 40%. Why this increasing trend cannot be simulated by all the GCMs in the colored lines. So how the dust emission relate to the anthropogenic activity? They are wind erosion, dust due to the wind erosion, which are caused by the land use change. Here showing the agricultural activity, the agricultural expansion is generate dust, and also poor water management caused the generate dust. And there are also directly emitted dust due to the anthropogenic activity like the agriculture activity and the construction and the traffic. And the third type is the anthropogenic dust is due to the emission due to the relate to the climate change, say like increase the wind and reduce the soil moisture and change the vegetation cover change due to the climate change. And a previous study by Genox 2012, based on the MODIS dust oblique depth and land use data set, they find out the land use change induced anthropogenic dust or AD. They find out in the Great Southern Great Plain and here's India and Middle East and Sahel and Central Asia and North America, Northern China is this source for anthropogenic dust. These sources account for about 25% of global dust emissions. Okay, so our study, we aim to represent the uncertainty dust, which due to the agriculture activities in the DOE's energy X scale Earth system model called E3SM. And in the E3SM model, the dust emission are based on the Zander et al. 2003 parameterizations. So you can see the F is the emission flux. It's a function of the the tuning parameter T here, and S is the soil erodibility, and FM is the grid cell fraction of exposed bare soil, and alpha is the sandblasting mass efficiency, and the QS is the total horizontally saltating mass flux. So this is the used in the default E3SM model. In our study, we modified that parameterization to introduce another term. This is due to relate to the uncertainty dust, so we call it AD. And so we break into the two terms. One is the AD, and the other one is natural dust, the ND. And we modified the FM, where is the grid cell fraction exposed bare soil, and then we this FM is a function of the leaf area index, and we sing out the FM from the cropland. So this is the we call the FMAD, and when it does the agricultural activity, and then the rest of the planetary function type PFT is using in another category as the natural dust. So this is the United model. We modify that, and we also and we also modified the QS, and we tuned based on the soil moisture. So we have this is for the AD. Yeah, so if we use by using different land use data set like PD and PI, we can investigate the dust emission in the past and in the future climate. And so I'm going to we run the model, the E3SM model, in two experiments. One is the controlled model, so we're using the default model, then the new dust parameterizations. It's called a new experiment. Then from the 2001 to 2010 simulation at 1 degree and 72 vertical layers, and the wind is notched to the Meratura analysis data, and then both simulation use 2000 land surface data set in the land component of the model, and then additionally we add a separate tracer for the anthropogenic dust, so we can in the new simulation then we can explicitly track it in the model. Okay, so I'm showing that, this is from the model, the dust emission, and in the present day, PD, and this is from control experiment, and this is new experiment. So we can look at in the new experiment, this is the ND, natural dust, and this is the AD, anthropogenic dust, and the total emission between the control and the new are similar, and why in the AD, for the AD emissions, we can see they are dust emission in the Sahel and North America and South Europe and the Middle East and in the northern China and India, which are missing in the control simulation. Okay, so these emissions are due to the anthropogenic dust contribute to the about 13% of global dust emissions. And then we compare our model simulation and to see if we modify dust parameterization that improved or degraded the model simulations. So then we compare the AeroNet aerosol orbit depth, and we select these AeroNet sites over the dust source regions. And then this is a control, this is the new. And this is simulated compared with the observation. You can see so if we compare the new to the control simulation, the correlation coefficient between the simulation and the observation enhanced, and also the mean bias is reduced. And we also compare with the US improved network, and this is showing the fine dust, and this simulated and observed, and this for cost dust. And in the blue one and is from the control, and the red is from the new. And you can see the new is showing the overestimation of the fine dust mass. While in the cost mode, the mean bias is reduced if you look at red compared with the blue for the cost dust. And we look at since we have the new simulation, we can look at the dust emission change from the pre-industrial to present day. We can use the pre-industrial land use, and see here is showing the crop PFT fractions, pre-industrial and the present day. You can see the increase of the crop activity of the in the present day. Therefore, you can see the estimated dust emission. This is enhanced from 220 telegram per year to the 567 telegram per year, by increased by 300 telegram per year. And why the natural dust doesn't change only much, only 4%. So then we estimate the estimated dust reinforcing due to the dust change from the pre-industrial to present day. It is had a negative forcing, negative 0.029 watt square meter. This represents 10% of the total aerosol direct radiative forcing estimated by the IPCC, which indicated this is that dust is a non-negligible forcing agent. And I want to say that from pre-industrial present day, our model showing the 12% increase due to the agricultural activity. And this we only represent the land use change, and we do not include the direct emission from the associated activities, and also we don't count the emission to the climate change, and therefore our increase is still smaller than the reconstruct dust data. And so we still the dust reinforcing may still be higher than our estimate. So this is the the summary. We represent the estimated dust emission related to the estimated agricultural land use in the E3SM V1 model, and we, according to our method, estimated emission account for about 13% of global dust emission in the present day, and the global estimated dust emission by 300 telegram per year, about 157% from pre-industrial to present day, which result at direct radiative forcing of minus 0.029 watt square meter. This is about more than 10% of total aerosol direct radiative forcing estimated by IPCC, indicating the non-negligible role of the dust in the regional and global climate change. And thank you for your attention.
Sorry, Xiaohong, Simone has a question.
Yes, so Xiaohong, nice presentation. Interesting that it makes such a big difference. Did you use the MEM4 model for this, or did you use changes in the course mode version of this model?
Yeah, this is the MEM4. Yeah, so we don't change add the dust. No, this is the E3SM model, not the CESM.
Yeah, but does it have the
E3SM model has different osmotic standardization from the CESM. Let's keep the CAM5. The E3SM use the CAM5.
Okay.
CAM5 the dust. Yeah, dust standardization very different. But I want to say that we haven't included supercosmo dust, and so maybe the supercos dust could induce the warming, and this is not accounted for in the current study. We have so this because the current model only have the dust until 10 micrometer size.
Thanks.
Any more questions from your question in the back?
Thanks for the nice talk. I was wondering about optical properties of anthropogenic dust and natural dust, because I guess compositions of natural and anthropogenic dust are different. Then maybe refractive index and shape can be different between these two when you calculate AOD?
Yeah, this is a good question. Currently, we only have one type of dust. You know, we haven't split the dust into different type. Like you have different dust mineralogy, so you can look at the different composition of the dust from AD and switching dust from the natural dust. Yeah, this is probably our next. Next, this is a very good question. We should consider. Right now, we're just using the same dust optic depth.
If there are no more, thank you, Xiaohong. If there are no more questions from the audience, I think are we switching over? Well, I have a quick question while they switch over, Xiaohong.
Yeah, please.
Your expressions for dust I couldn't see where the meteorology was included, like, for example, wind speeds. Do your emissions include some?
Yeah. So this is the Q. You know, I have a
Okay.
QS. Yeah, QS is depend on wind.
All right, got it.
Okay, thank you.
Okay, let's start.
Yep.
Okay, yeah. Today I want to talk about our performance of the karma sectional aerosol model in CESM. And I want to acknowledge all the co-authors listed here. A lot of work went into this. So what we have done, we have now coupled CSM to the CSM2 version 2 to the community aerosol and radiation model for the atmosphere karma using the sectional aerosol model. And I haven't noted it here, but this is work that has been done by Ping-Fei Yu in the past. He has implemented karma, a very similar model version in CSM1, and now we have performed it in CSM2. What we have done, we have we can now have a configuration where we fully run karma, which is coupled to all those components that you can see here. So there's no MEM running. It's just substituting the MEM version to the karma version. And you can see here on the right, this is a number size distribution in the lower stratosphere. These are atom observation. And that illustrates the karma model. There are two groups we are using. We have a mixed aerosol group, which is described of 20 bins. And the mixed aerosol group includes all the aerosols, mostly in the troposphere, sea salt, dust, like carbon, secondary and organic aerosols. Then on the blue, you see the pure sulfate group, which is most important in the stratosphere. This covers mostly stratospheric sizes, as you can see here. And you can see that the model is nicely representing the size distribution that is observed. And on the bottom here, we do have also MEM included. These are the three modes. For sulfate, we have MEM4, but really MEM4 includes three sulfate modes, or three modes, and a primary carbon mode that we don't show here, which is very similar to the accumulation mode here. But so the idea is that we have implemented this model, and we want to now go and look at the results, and we are in the process evaluating the model based on observation and really having a tool to baseline the MEM model that we are using. So we're expecting that a more comprehensive model with more traces like karma will maybe have better microphysics and represent results better. So what we did is we developed two sets in CESM2, the Wacker middle atmosphere model. We're using a 2-degree horizontal resolution. This is a 70-layer model. And then we have the ChemChem model, the 32-level model on 1-degree resolution. And we performed various simulations with those simulations, mainly focusing on the Mount Pinatubo period, so after Mount Pinatubo eruption in 1991. And then also for baselining the model for background aerosols and later small volcanoes from 2000 to 2020. And as you can see for the performance, we're actually for ChemChem having 220 aerosol tracers compared to a normal ChemChem of 20. 7 aerosol tracers. This certainly increases the computational effort, but it is still reasonable to run this model, also the middle atmosphere model, so we can actually run it for many years, even though we are representing that many tracers in the model. And so the first thing that we looked at was the Mount Pinatubo period. Can we simulate Mount Pinatubo well? And on what you can see here is a extinction from a Glossop data set. That's climatology that was derived. And this is an average between January to March 1992, so about 6 to 9 months after the eruption. You see the high aerosol extinction here. And what you can also see is that with standard injections that we use in CMIP 6, there is actually the magnitude may be right, even in MEM4, but really we see that the distribution isn't right. We have too much aerosol in high northern latitudes. And actually, Glossop is underestimating the peak, but it's still, this doesn't look right. We also don't get aerosols move into the southern hemisphere. And then we ran KARMA, and we're even more disappointed to see even a worse representation. But then when we looked into this is really because of how the microphysics work in KARMA. MEM has a not very small accumulation mode, and so many, as soon as aerosol form from the injection of sulfur, they go in a Icon mode, in a mode that really fast grows and has more aerosols that can stay in the atmosphere. But what we decided is that really a column injection that we used in MEM in the past is not really representative of the volcano, and when we use a 100-kilometer model like we have. So what we really need to do is regional spread out injections that we tested. And so now we're spreading out injection of Mount Pinatubo aerosols from -5 south to 15 south north, instead of just at a point injection in 15 north. And then you get a much better representation in MEM. And then looking at KARMA, we also get a much better representation, and we also increase the amount of injection a little bit higher, because for MEM we were always on the lower side. So we think that KARMA is representing now Mount Pinatubo quite well. And now looking at what the stratospheric aerosol distribution time series, you can see 2 observational data sets, one the Glossop data set that I showed before, and another data set that seems to be having a higher peak, as I said before initially. And what we can see, this is when we did the column injections before KARMA underestimated this distribution. But if we do regional injections, we are improving this. And if we increase now our injections, and we also change to a different nucleation scheme, and I can't go in this talk to this, we're getting a really good distribution. But to really evaluate this, and that's why we're using a sectional aerosol model, we want to look at size distributions. And what you can see here is the size distribution, again in March, like 9 months after the volcanic eruption. This is balloon data over Wyoming. We have samplers that sample an accumulated number distribution, meaning you start sampling the largest bins and then you accumulate the bins to have the largest number, the total number here. And so what you can see is that KARMA, our pure sulfate mode, which is most important here after the eruption, is representing the size distribution quite well in this area, while MEM is somewhat underestimating it. And we can also look at something that is more a volume size distribution that indicates where the mass is of the aerosols. You can see that KARMA is showing most of the mass here in the higher mode, and MEM is not really able to capture this same size distribution. The mode is too small, and we just have smaller aerosol sizes, and we can see that they're actually underestimated compared to observations, and KARMA is performing better. Also, the Icon mode in the stratosphere is overestimating the smaller particles. So both models are not perfect. Also, KARMA seems to overestimate the really largest bin. So we're still working on extending the pure sulfate mode in the future. But if you think about we're using this for doing geoengineering studies, we really have to do better here to represent probably large injections and really improve the uncertainties in those models. So then we did look at stratospheric background. We did run a 2001 to 2020 simulation, and you see all the models actually represent stratospheric area D quite well compared to the observation, the black line. And looking again at the size distribution, we do see, again from the Wyoming balloon observation, this is now background aerosols in 20 kilometers, so in the stratosphere. Again, MAM is actually overestimating these larger sizes. You can see this here in those modes. And while Karma is, in this case, doing a pretty good job, I'll do show other places. And it's not always that Karma is better than MAM, but that shows that we do have a better representation. We did look at tropospheric AOD, and David Fulmore has processed these really nice data sets for Terra and MODIS from 2001 to 2020. This is for summer in this climatology. Down here is Mera, and then we have Karma here on top and MAM4 on the bottom. And you do see differences, and on the right, it's easier with the difference plot. We do get a better representation of the southern hemisphere here in this in summer, while there's some underestimation in Karma still at different places. I think we are improving some of the biases that were in the MAM models, really the high aerosol burden. This is from dust in the, say, on the top of Southern Africa and Australia. And this is really what we talked about, why we want to change to MAM5 or to a different sigma level for CHEM, because the smaller mode in the dust does not represent aerosols well, and that causes some of these things in MAM4. So there's things to improve in the model. Some of the we have a really nice campaign, the Aircraft to ATOM campaign, that had sampled around the globe. And the goal here is to just really evaluate the background aerosol for now. So what we are doing, we are focusing on two regions, the Pacific over the ocean here and over the Atlantic, and we're picking three regions, 30 north to 60 north, 30 north to 30 south, and then the southern hemisphere, 30 south to 60 south, and sampling all those aircraft campaigns to compare to the model results. And I have a few now comparisons here. This is, for example, sea salt. What we can see is Karma in red, and this is averaged over those regions. As I said, Atlantic is on top, Pacific on the bottom, the tropics is in the middle here. So what we can see is that Karma in red does do, in general, a better job for sea salt to represent the surface values. We do have a different sea salt emission model in Karma than in CHEM, so that's part of it. We do see that the overestimation in the southern hemisphere is reduced, which is important potentially for radiation. And other places may be not as good, like in the northern hemisphere. We have to look into this more. And then we're looking at dust. This is, again, we are improving the high bias in the southern hemisphere, while in general, we see very similar distributions. There's a bias here compared to the ATOM data in the tropics over the Atlantic. And again, this is really just first looking at the general picture and not looking at the details yet. This is more work we need to do. For sulfate, we're also seeing somewhat an improvement in Karma in the magnitude. We're still seeing an underestimation over the oceans. We don't, in both model versions, include yet the marine organic sulfates in this model version, so that may make a difference. And one thing I should say is we just found a bug in the Karma model to prescribe some of the sulfate. There shouldn't be sulfate emissions, but we have some due to some part. And so there may be some changes in this, but I don't think it will change very much in the comparison. We'll have to see. But anyways, we're thinking that in general, this is a very useful tool to have Karma compared to MAM. Now we can look at the size distributions again. And here I don't show the Pacific. This is just the Atlantic. I'm looking at 30 north to 0 and 0 to 30 south. So what you can see is really the dust over, which comes from Western Africa in this distribution of Karma, where there is some underestimation again in MAM to really cover some of these sizes because of how the modes are structured. And that's pretty interesting in other places. Another shortcoming in Karma actually is the upper troposphere. We see that there's an underestimation in these regions in the tropics where the ICAM mode in MEM covers the numbers much better. And we think that the mixed aerosols here, especially the nucleation of S or A secondary organic aerosols, is not covered when our mixed aerosols start at ranges that are basically too high. What we can do easily in Karma is change the size distributions. I mean, we can easily change this, but then of course we have to evaluate the model. So we're working on probably changing these size distributions to improve this situation. And then as a summary, conclusion is more work, but I think we already have a really good representation to use now. People can use it, it's on GitHub. Well, after probably we fix that bug, which should be, it's done quickly, but what we think there's a lot of more work that can be done. There's so many karma models actually out there, like Wenchen, Chuck, and others developed karma models that are not yet included in this version of CSM. Volcanic ash, we heard a talk on Monday, maybe karma is a good tool to use that. Meteoric smoke, improved PSCs, and so on. I don't know what my time is, but okay. Yeah, so yeah, and for ChemChem, as I said, we do really want to extend maybe the sizes of the mixed aerosols. There's more work that can be done in both models for the washout and heterogeneous freezing schemes. And definitely the next step is that we still have to couple karma to the land and ocean fluxes, but then we really want to, we already ran an AMET style simulation, which looks very reasonable, but we want to couple it the first time to really the ocean and have a climate model so we can do simulations that are fully coupled, like geoengineering simulations and other things. And that's the next step. Thanks.
We have time for one quick question.
You can do Earth, isn't it?
Okay.
Oh, so this is really a layman's big picture question. So you mentioned Wacom and ChemChem, but then how about Chem? Is there like a vision to replace MEM, or do you plan to keep MEM? So what's the plan?
Well, MEM is always kept. This is basically a parallel aerosol model that you can always use. And actually we can work on a chem configuration. That is possible. It hasn't been done. It hasn't been our priority, but it is something we can work on and do. It is basically just some more work to add a chem karma.
Okay.
And if there's interest, we can work on that.
I was just curious, what's your vision about aerosol in Chem?
Yeah, no, I think the question then will be, I don't know, how do we do chem prescribed aerosols in the stratosphere? Questions like that have to be addressed because, yeah, chem is much simpler, but it is, I think it is possible to do, yeah, but we'll continue having MEM in the model as a standard model.
Okay, thank you.
I think we should move on,
Yeah, sorry.
because we're 5 minutes late. Our next talk is from Lu Wang. Oh, are you here?
Yeah.
Okay.
I am here. That's a good question.
My schedule doesn't say whether you'll be in person or remote.
Which one is yours?
I forgot to.
You don't have your talk?
I do.
It would be the fourth one.
Number
No,
4?
above.
Okay, this one.
Yeah.
There. All right.
Oh, maybe I should give you magic.
Simon talk about karma sectional model for aerosol, and I'm going to talk about using karma, the sectional model for clouds. My name is Lu. I'm a grad student at CU. My advisor is Brian Toon, and Yun Qian and Chuck helped me a lot with this project. So first, just introduce the macrophysical process in the karma cloud model. basically we have two major components. One is Karma liquid, the other is Karma ice. For Karma liquid, it ranges from 0.3 micron up to 4 millimeter, the raindrop size. And Karma liquid interact with water vapor for evaporation and activation, condensational growth, then further growth of coalescence growth with itself. It interacts with Karma ice for freezing and melting. For the Karma ice group, it interacts with water vapor for sublimation and deposition, and with itself for coalescence growth. The Karma ice can interact with MEM for interstitial dust for heterogeneous deposition of dust. It also interacts with MEM for interstitial sulfate for homogeneous nucleation of sulfate. Then it also interacts with MEM for cloud-borne black carbon and dust for immersion freezing. So far, that's the current microphysical processes we have in Karma cloud model. In the future, near future, we will include ice multiplication, and then we can easily add in the grapple group. So this slide is about the basic flow during the standard CESM 30-minute time step. During this 30-minute period, we call multiple times for dynamics. Then we have 3 calls of this micro and microphysical loop. So in one of these magmic loop, we call club once with 5 minutes step, followed by MEM aerosol with a 10-minute step, then followed by Karma with a 10-minute time step. The club MEM for Karma interaction is very important here, but it's not very obvious in the code. And the following couple of slides, I'll show you some preliminary results from the Karma liquid part. So basically, I'm trying to compare Karma with MG and MODIS retrievals. The Karma is a sectional, MG is kind of model. So, and MODIS is the observation. So basically, the color scheme, if you take a look, black for Karma, blue for MG, and red for MODIS. The left panel is for results over land. On the left is over ocean. So it's just a comparison of daily output. You can see the black Karma PDF, effective radius PDF. We get a lot small droplets. So now we kind of realize we over activate drops, like activate too many small cloud drops. And over ocean, it's not that bad, probably because over ocean, the total number concentration is not as big as number concentration over land. And over ocean, you can see we see a lot large particles than mg. And this following slide is also about effective radius. It's a global map. On the top is karma. In the middle is mg. And the bottom is the MODIS image. So you see a lot white space here, because when I tried to do the plots, I did some data screening first. When the number density and the mass mixing ratio are too low, I excluded those data from model output. That's why you see a lot white space. If I don't do this data screening, you won't see so many white space. And the white strips on MODIS image because the satellite swap gaps. So basically, you can see the red area here represent a larger droplet. The karma and MODIS image kind of lined up, which is a good sign for us. So that's the size. And this next slide is comparison for the liquid water content. So basically, these two, one from karma and the other from mg, directly from model, and this one from Huang et al. 2015 is observation data. So the color scale not quite the same, but just let you know this red, this blue area here, kind of close to the green to blue color area. So as you can see, we kind of get bad in the tropical area. The convection kind of collapse is it's quite common in our current simulation that we are trying to figure out. Also, another possible reason we are thinking about is like when our freezing is too aggressive, so the water just collapse. And you see a lot large high values here because we also include water from drizzle and rain. That gives us some high values here. And this slide is liquid water path comparison. So on the left is the map. On the right is the PDF. I excluded all the liquid water paths lower than 20 gram meter square. So as you can see, we have quite a lot large liquid water path values there. The reason, again, because our liquid also include drizzle and rain in it. So that's comes to the hard part for comparison, because we know MODIS cloud drop only go up to 30 micron. And for MG, it has a cloud part and the rain part. And for us, we kind of mix everything together. So if there's a mismatch there, it doesn't mean like things going wrong. It's just that we are comparing different things. And if you look at the PDF distribution, like we have a lot high values, possibly also contributed by drizzle and rain. So that's the end for the Karma liquid. And the next couple slides for some results from Karma ice. And this is ice water content from Karma, MG, and some observational data. The model image is just a daily simulation. The observation is actually a couple years average. But as you can see, we are kind of good at the color scheme for high values. These three images are kind of match each other. So you can see at mid and high latitude, our simulation kind of gets better, but we are very bad with the tropical deep convection area, and we haven't figured out why yet. And MG is better than us in the tropical area, but the value is still kind of low. And this slide is a slide for precipitation. So it's the large scale precipitation, left Karma, right MG. You can see they are kind of similar to each other with regard to where we get precipitation. Like, for example, the South US and desert area, like we don't see much precipitation there. However, we are lacking of this kind of baroclinic patterns in MG. We just realized and haven't figured out what happened yet. So just to summarize, for liquid droplet, we have expanded the size range to drizzle and raindrop size. We solve a coagulation equation directly instead of using autoconversion. The droplet simulation looks better over ocean than over land. And so second is a problem we realized. We feel like the activation process, the aerosol karma, modal aerosol karma activation process may be overactivate a lot of small drops, and we are trying to fixing this now. Also, the tropical deep convection will collapse over time, but we haven't got any clue on this yet. And we are planning to add ice multiplication for Karma ice in a very near future. And compare CESM to Karma with CESMG, CESM2 MG. We are several times slower than MG, but our goal is to better get the microphysics done. So that's all. Thank you very much. Any questions?
Very
Yeah.
late, so I think we're just gonna have to unfortunately move on to the next talk. Thanks very much.
Thank you.
Our next talk is by Zheng Lu, who should be on remote. You should share, yeah, okay.
Can you hear me?
Yes.
Okay. Hi, everyone. My name is Zheng Lu. Today I'll talk about examining the impacts of interactive fire polymerase model in E3SM on aerosol-related effect. As you can see from the title, this work is done in E3SM, but it can be easily transplant to CESM. So this is a teamwork before Texas A&M University and PNNL. Motivation. So we know the biomass burning aerosols are very important for global climate. They account for 3/4 of total global carbonaceous aerosols and 1/3 of global black carbon aerosols. BB aerosols can greatly alter the global relative energy budget through aerosol radiation interaction and aerosol cloud interaction. For some same amount of BBA, the relative effect greatly depends on the injection height of BBA. For example, the direct effect and semi-direct effect can switch signs depending on the relative position of biomass burning aerosols and clouds. In addition, in the future, we expect to see more extreme fires, and they will cause more BBA injected into a higher altitude. Despite the importance of accurately representing injection height of biomass burning aerosols, the vertical profiles of BBA are usually prescribed in most GCMs as function of geolocation and seasons. The goal of our study is to replace this prescribed vertical profiles with online interactive calculation. In our study, we successfully incorporate a 1D polymerase model developed by Freitas 2007 into E3SM. The polymerase model is familiar to the community because it has been incorporated in WolfCam and used in many studies. The model solves 6 equations of vertical velocity, temperature, and the cloud hydrometers. So the model requires fire size and fire heat flux, as well as the ambient thermal conditions from the host model. So we made several changes to the polymerase model so it can be smoothly coupled with E3SM. Firstly, the study by Martin 2012 tested several techniques for estimating fire size and fire heat flux. We follow their approach and use 10 times fire radiative power, FRP, for the heat flux. And to estimate the fire size, we use a scale to maximum FRP technique. So within 1 GCM grade, the resolution is, if it's 1 degree, the fire intensity can vary significantly. So the injection height also vary as shown in this picture. So we partition the total fire emission in 1 grade into 4 intensity bins based on the FRP values. Then we perform the polymerase calculation for each FRP bins individually. Finally, we also apply a Farad Dano cycle, followed the study by Li et al. 2019. So to conduct simulation, we use E3SM V1 with NE30 grade. We prepare 2018 QFED daily fire emissions together with 2018 MODIS FRP retrievals. Here we design 4 experiments. In the control experiment, we have default vertical profiles. The Farad Dano cycle kept constant. And we also, in the plume experiment, we employ plume rise calculation and apply this Farad Dano cycle assumption. Well, in this no Dano cycle case, we just keep the Farad Dano cycle constant. To mimic the CESM, we also have a case surface in which we put the biomass burning emission directly at the surface. So for each experiment, we conduct both 1-year nudge simulation for validation purpose and also 10-year climatology for studying the radiative effect. Need to mention the same biomass burning aerosol emission fields are used in all these experiments. So move on to the results section. Let's first look at this example of polymerized models performance. This figure shows the vertical profiles of BBA emissions in North America during August. This 24 dashed lines with color sprite represent the Dano cycle of biomass burning aerosol emission vertical profile. The variation of the vertical profile in these 24 hours are very strong, you can see. During the local night, when the PBL is low, the BBA are mostly emitted below 1 kilometers. While during local afternoon, the BBA are injected much higher, with the profiles peaking around 2 kilometers. The solid line here shows the monthly averaged vertical profiles of BBA. The control case in blue, plume case experiment in red, and the no Dano cycle in green. The result shows that both vector, the polymerized calculation and the Farad Dano cycle are very important in terms of emitting more biomass burning aerosol above 2 kilometers. So we further evaluated the injection height modeled by E3SM against the miser plume product. Many thanks to Dr. Van Marty, who gave us the miser product. However, I should emphasize that the product is for 2008 to 2010. The figure shows the percentage of biomass burning aerosol injected higher than 2 kilometers in GJA period. Please note that the miser only measure the plume around 10:30 local time. So therefore, for plume case, we also show the result around 10 local time and 11 local time. The comparison shows that control experiment significantly underestimate the emission height in most region of North America. The only exception is the Alaska, where the control case overestimate the percentage by 10%. Another region, where control case significantly overestimate is South America. So we can see dramatic change in the percentage field from 10 to 11 local time in plume experiment. This also a time of day when the PBL dramatically change. So by averaging the 2 time slice, we found that the plume experiment performs reasonably good over the most regions. However, they overestimate the BBA injection height in Central Asia and Southeast Asia. So in July, August 2018, the BBA plumes in North America are in situ measured by NOAA Weekend campaign. So in this slide, we compare vertical profiles of medium biomass burning aerosol mass mixing ratio with the measurement. So the hourly model outputs are sampled along the flat track for fair comparison. So the x-axis shows the medium organic matter mass mixing ratio. The black line represents the measured values. So in July, we can see measurements show two peaks, one around 4 kilometers, one around 5 kilometers. So including the plume rise calculation alone is important for capturing this peak. However, only the experiment with both plume rise model and fair dynamic cycle assumption can sort of reproduce the second peak. The altitude is underestimated by about 500 meters. In August, according to the observation, so there's a peak at 3.5 kilometers, while the peak in three experiments 500 meters lower in altitude. So meanwhile, the plume experiment outperformed other two experiments and reduced the overestimation of BBA aerosols under 2 kilometers. Lastly, we examine the relative effect associated with the plume rise calculation. The results shown in this slide are from the climatology simulations. So the upper panel shows the difference between the plume and the control case experience, while the lower panel shows the difference between plume and surface experiment. The figure on the left shows the difference in AOD associated with black carbon and POM, while the total relative effect at TOA on the right. So we found that the plume experiment predicts slightly higher global average AOD. The AOD difference field show many dipole features like in North America, in Southern Africa, and in Siberia. It's because when emitted to different altitude, the transport route will be changed. So the inclusion of a plume rise model can lead to a 0.13 watts per meter square warming effect. This because the surface albedo effect and the semi-direct effect of biomass burning aerosols. The surface albedo effects due to more BBA transported from Siberia to Arctic. The semi-direct effect is due to more BBA injected above cloud layers. Comparing the plume and the surface case experiments, the AOD difference is significantly large, and we see positive change everywhere. So this is easy to understand because when emitted to surface, the aerosol can much easier to be deposited. Such large difference AOD is to significantly increase in cloud droplet number concentration. As a result, we see a strong cooling of minus 0.14 watts per meter square. The results shown in this slide kind of interesting to me because the injection height in the plume case is the highest among the three experiments, then followed by the control experiment. However, the relative effect is not a linear response to the injection height because the different roles of aerosol relative effect. So to summarize, so in this study, we incorporate interactive fire plume rise model in CESM, and the model performs the case with plume rise model, and fire dynamic cycle outperforms the default model compared to the in situ measurement, and and the inclusion of plume rise model causes strong warming effect. The relative effect is sensitive to injection height in a non-linear manner. With all, I thank you for listening.
All right, thank you, Zhang. We are into our break. I suggest if there's a quick question, please ask it. Anybody who feels like taking their break now, I would suggest you do that too. We have a short session after this, starting at 2:30. It's only 3 talks. So I suggest we just restrict ourselves to a short break and come back at 2:30. So are there any quick questions? All right. Well, thank you, Zheng. Your email's on your slides.
Thanks, my friend.
Can you share your presentation? Or would you rather that I try to share it here? Okay.
Can you see my slides?
Yes.
Okay, good.
All right.
So shall I begin? Hello everyone, my name is Xi Zhao. I'm a research scientist in Dr. Xiaohong Yu's group from Texas A&M University. Recently, I'm doing some research about aerosol cloud interaction. Today, I would like to, the title of my presentation is Increase cloud liquid water in climate models, enhance both aerosol indirect forcing and cloud radiative feedback. So this slide shows the motivation for us to do this work. In this figure, the y-axis is showing the effective radius forcing of anthropogenic aerosol. From this figure, it is most climate model from CMAP6 showing a negative value, indicating a cooling effect from the anthropogenic aerosol. The x-axis is showing the cloud feedback, representing the response of cloud to climate change. Most climate model indicating a positive cloud feedback, which showing a warming response of cloud to climate change. So in this figure, there are some relationship between the ERF ACI and cloud feedback. When they note that the climate model with a stronger positive cloud feedback also has a stronger cooling from the aerosol indirect forcing due to the anthropogenic aerosol. And we are wondering why there is such a relationship between the ERF ACI and the cloud feedback. Therefore, we conducted a series of simulations. The purpose of those simulations is try to perturb the glaciation of the cloud, and then to see how the ERF ACI and the cloud feedback will change accordingly. So we use the E3SM and the CESM model. The control simulation is using the default CESM and the E3SM model. The DCS simulation is same as control, but we change the threshold value on cloud ice to snow auto conversion. The convection trigger simulation is the same as control, but we use a different trigger in convection scheme. The SIP simulation is based on control, but we add in 2 additional secondary ice production mechanisms into the climate model. The M92 simulation is based on control, but we use a different ice nucleation scheme in mixed phase cloud. The freezing cloud simulation is an extreme case. In this simulation, we assume all the condensation to be ice phase, and the cloud temperature is smaller than -5. So in this simulation, we will not have the mixed phase cloud. We only have the ice phase cloud when the cloud temperature is smaller than -5. So with different modification, the cloud liquid decrease and the cloud ice will increase. So in the model, this slide shows how we calculate the ERF ACI and cloud feedback. In order to calculate the ERF ACI, we need a pair of simulation called PD and PI. In the PD simulation, we use the aerosol emission from the present day. In the PI simulation, we use the aerosol emission from the pre-industry. A method from GAN 2013 is used to calculate the ERF ACI. In order to calculate the cloud feedback, another pair of simulation is needed, called PD and PD plus 4K. The PD simulation uses the sea surface temperature from the present day. The PD plus 4K simulation uses its sea surface temperature has a unified 4K compared with the sea surface temperature in PD simulation. A diagnostic package developed by Zalinka is used to calculate the cloud feedback components. So next, we will move on to the result part. Firstly, I will show the relationship between the liquid water path and ERF ACI. We first look at the zonal mean distribution of the liquid water path from the different simulation use the CESM model. It is clearly that the control simulation has the highest value of liquid water path, while the SIP and the M92 simulation has a medium value of liquid water path. The freezing cloud simulation has the smallest amount of the liquid water path. So this figure shows the relationship between the liquid water path and the ERF ACI. It is clearly that the liquid water path and the ERF ACI has a linear relationship. Their correlation coefficient is minus 0.9. We notice that with the increase of the liquid water path, the ERF ACI is decreased. Considering the ERF ACI has a negative value, it's indicating that the model will have a stronger cooling effect from the anthropogenic aerosol when the liquid water path is increased. So next, our analysis will focus on those three experiments, which represent the low liquid, medium liquid, and high liquid scenario. So as shown in this figure shows the horizontal distribution of the liquid water path. It is clearly that with a stronger glaciation process, the liquid water path decreased significantly, especially over the storm track in the mid-latitude northern hemisphere. And accordingly, the ACI is the aerosol indirect forcing become weaker in the mid-latitude northern hemisphere, where the anthropogenic aerosol has the largest emission. It seems that with smaller liquid water paths, the clouds are less sensitive to the aerosol perturbation. So this is the unique of our study. Previous study investigate the ACI from an aerosol perspective. They analyze how the aerosol change will influence the aerosol indirect forcing. Our study is from a cloud perspective. It shows that even with the same change of the anthropogenic aerosol, the state of cloud can largely influence the aerosol indirect forcing. This is further proved by detailed analysis of the cloud property. This figure shows the vertical cross-section of the changed liquid water content from the PD to PI. The x-axis is the altitude and the y-axis is the pressure. The first figure is from the high liquid simulation. The second figure is from medium liquid simulation, and the third figure is from low liquid simulation. The shading shows the changed liquid water content from PD to PI. The black line shows the temperature. So we know that the low liquid experiment, which has a stronger glaciation process of the cloud, those stronger glaciation process not only freezing the available liquid cloud in the cloud, it also freezes the cloud water enhanced by the anthropogenic aerosol. Therefore, those simulations with a stronger glaciation process has a smallest increase of change the liquid water content from the PD to PI. Similar conclusion is with the analysis when we analyze the changed cloud number concentration from the PD to PI. So next, we look at the relationship between the liquid water path and cloud feedback. This figure shows the relationship between the liquid water path and cloud feedback. The correlation coefficient is 0.94. It is clearly that there is a linear relationship between the liquid water path and the cloud feedback. With a larger liquid water path, the cloud feedback becomes more positive. We further separate the total canal feedback into different components. It is showing that the optical depth canal feedback dominate the total canal feedback. The mechanism is well known by the community. The simulation with less liquid will have more, always have more ice. Under a warming condition, those more ice has more potential. There will be more potential ice melting to liquid. Considering the liquid droplet has a smaller size, therefore it has a it will increase the canal optical depth. Therefore, will reflect more short wave radiation back. Therefore, has a stronger negative canal feedback. So at the end, we also look at the relationship between the ERF, ACI, and the canal feedback. We noticed that consistent with the previous study, we also noticed a linear relationship between the canal feedback and the ERF, ACI. The simulation with a high liquid water pass always have a more positive canal feedback and a stronger cooling effect from the ERF, ACI. Those the warming effect from the canal feedback and the cooling effect from the anthropogenic aerosol tend to offset each other in the 21st century. So to summary, our new finding is we noticed that the ERF ACI decreased with the increased liquid water pass, indicating a stronger cooling effect with the increased liquid water pass. We noticed that the simulation with larger liquid water pass, the clouds are more sensitive to the aerosol perturbation. Which shows that it is a liquid water pass link the aerosol indirect forcing and canal feedback together. We also consistent with previous study, we also noticed that there is a positive relationship between the liquid water pass and canal feedback. Thank you for your attention.
We have time for one or two quick questions. Let's see if there's anything online. I don't see questions online.
Talking.
Hmm?
Trying to ask
Yeah.
a question?
I don't think so.
Oh, okay.
He's the next speaker.
No, he's the speaker after.
Oh, he's after Christina.
He's been talking for a couple of minutes.
Thank you, Shi. Thanks for the presentation. I think we'll go on to the next talk by Christina McCluskey.
I don't know what I need to do.
Probably in the folder.
There we go.
We just need to get it on the screen.
Oh, yeah, I'm working on that. I'm on my way.
Okay, thank you. I'm Christina McCluskey. I'm a project scientist here at CGD. And today I'm talking about CAM6 ice formation over specifically the Southern Ocean mixed phase clouds, but some of the findings I have here are also relevant to other remote regions like the Arctic. The takeaway from today's talk is that heterogeneous freezing of rain and rime splintering are dominating ice production in CAM6 Southern Ocean mixed phase clouds. And I think this is unrealistically masking sensitivities to aerosol ice interactions in CAM or CESM. For those of you who are joining because of the title, to quote Vanilla Ice, stop whatever it is that you're doing and collaborate and listen. In all seriousness, you can do your email if you don't have any interest, but I do think that this is important. And if you don't understand anything that I just said about our key takeaway, hopefully we can get there. The clouds I'm talking about are these beautiful stratocumulus decks over the Southern Ocean. This is a video from the Socrates Field campaign a few years ago, 5 years ago now. And the Southern Ocean is a special place. It's pristine. It's about 80% cloud cover annually. And these clouds are very optically thick and participate in the climate system in an important way. And I think she's talk actually did a really good job of motivating this work, highlighting how important it is to properly represent mixed phase clouds. When I think about Southern Ocean ice phase aerosol cloud interaction, so I'm not talking about CCN, I'm talking about ice nucleation. Over the Southern Ocean, it's a little bit of a simpler problem than a lot of places around the world, where we can assume that our ice nucleating particle population is primarily composed of sea spray aerosol emitted from the ocean surface and dust transported from long distances. And these particles, these ice nucleating particles, will participate in ice formation through heterogeneous freezing. So there's a few different pathways in which this can happen, kind of depicted here in this cartoon. But the primary pathway we think is the immersion freezing pathway. So these particles will form a cloud droplet that's supercooled, and then it will be nucleated into an ice crystal. And this process happens between 0 and 40 degrees Celsius. So it's quite a wide temperature range, and the Southern Ocean clouds are often within this temperature range. And once you start the formation of ice, you have a lot of subsequent processes that take off in the microphysics, and one of them being secondary ice production. And just to highlight that CAM does include rime splintering, but there are several other mechanisms that currently aren't accounted for in CAM. And then I just want to add in, CAM 6 Southern Ocean clouds are definitely better than CAM 5, if anybody's been paying attention to the Southern Ocean over the last few years. But we do still see underestimates of ice. So this is showing a comparison led by Andrew Gettleman, looking at the Socrates Field campaigns. These are nudge simulations with CAM 6. And you can see pretty good agreement with cloud water content. When we look at ice water content in the far right, so you can see the observations are highly uncertain, but we also see very low ice water contents in the model. So there's some indication that we may not be completely carefree when it comes to the Southern Ocean. So my hypothesis I've been driving for probably almost a decade now is that marine IMPs are responsible for the onset of ice formation in the Southern Ocean low-level clouds. And marine IMPs, or ice nucleating particles, are not currently accounted for in CESM. And so as part of this DOE project, we are testing and implementing IMP parameterization that includes marine and dust aerosols. So that's under review right now. And then we also want to determine the impact of marine IMPs in Southern Ocean cloud properties. And like many proposals, sometimes people beat you to the punch. So we've got a couple of studies already out that are highlighting that there is sensitivity of the Southern Ocean. So this is a paper from around 5 years ago now that really highlighted, in this particular model, strong sensitivity to how you represent ice nucleation in the model. And more recently, there are studies that are coming out that are showing that there is no sensitivity. So this is actually from Xi Xiao's work, looking at shortwave cloud forcing and longwave cloud forcing with CAM 6. And all these different colors, I don't put all the details here, mainly they're changing the ice nucleation, including marine IMPs, and they're not seeing a lot of changes. And I've repeated these experiments, I get the same answer. And so now the studies kind of shifted a little bit, and now we're thinking, okay, why are these Southern Ocean clouds insensitive to heterogeneous freezing of cloud droplets? That's what I want to know. I'll be running, or I have run model simulations using a kind of more recent tag that has a couple updates that are useful for the analysis I'm doing. I'll talk about. It's a coarse resolution model. We're still using the 32 levels. And I'll say that we have mostly the same, or we have the default physics in CAM 6, but I am changing the heterogeneous freezing scheme. And so in CAM 6, what controls ice processes? So heterogeneous freezing of cloud droplets is part of that. And I've broken that out to kind of explain these different mechanisms. But like I said, we really care mostly about this immersion freezing in these clouds. And so in your default CAM 6 model, you'll have the stochastic, hi. Sorry, don't mean to interrupt you. It's okay. Share your screen really quick. Oh, wow, okay. Oh, that's sad. Sorry, everybody online. Oh, okay. Hopefully they can see now. In default, CAM6, you have the stochastic ice nucleation scheme or classical nucleation, CNT. There's a lot of different names that people call it. And when you turn that off, what comes in is our big temperature-dependent, big BIGG, not large, temperature-dependent ice nucleation scheme that was used in CAM5. And then I'm introducing this new deterministic marine and dust INP parameterizations, which are shown here. And these are, the reason why I'm in favor of these is they're a little bit more straightforward to compare to observations. And so, and we also have a parameterization for marine aerosol. And so this is just based off of aerosol simulated by MAM4. And that's how we are introducing ice nuclei into the model. And I'm going to try to go a little bit faster in case there's questions. And then there's subsequent processes to that initial heterogeneous freezing of cloud droplets. And so in the model, we also have a process called heterogeneous freezing of rain, which transfers rain to ice whenever rain is in supercold temperatures. And this follows another 1953 parameterization. There's ice multiplication from rime splintering, so that's secondary ice production, following a parameterization from 1986. And then a couple other processes that are loss processes for cloud ice accretion and autoconversion, and then of course sedimentation. So what have we done? Well, in this tag that I'm using, we have number tendencies. So before MG, so it's always been a 2-moment scheme, but we haven't had the number tendencies as tracers in the model. So we've added these in, and similar to Jesse, I just put this up here to show how much work we did. But I just want to say a special thanks to Cheryl and Kate, because they also were a big part of putting this into the model. But these number tendencies are really helpful because some processes will influence ice mass, whereas some processes may influence ice number, like secondary ice production would influence number more. And so we wanted this tool to be able to assess this problem. And so what I'm showing here now are vertical profiles averaged over the Southern Ocean region. So temperatures here, you can see all these clouds are in this mixed phase temperature range. And then here's our IMP number concentrations. You can see there are higher values of marine IMPs down below, and then higher values of dust IMPs aloft. And that these IMP concentrations are increasing as you get colder temperatures. So that's all working. And then we have number concentrations of the different hydrometeor types. Here I'm showing these ice number concentrations, which are quite low. You can see rain throughout the atmospheric columns. This is going all the way up to 6 kilometers. We have rain throughout the atmospheric column. And we also have cloud droplets. This is in per cc. So quite a lot of liquid in the Southern Ocean region. And when I look at number tendencies, this is on a log scale, just so that you can even see the immersion freezing cloud number tendency in this dark green color. And this is consistent, again, with the profile of the IMP number concentrations. That's great. But what really comes out in looking at these number tendencies is that the immersion freezing of rain process is really dominating ice production in terms of number, and also the secondary ice production process here. So for those of you who aren't as familiar with ice microphysics, really this secondary ice production, this purple line, is kind of an answer to that initial ice formation. So really what I'm concerned about is the immersion freezing of rain. That seems to be driving the initial ice formation. And so thinking about some observational context to kind of provide some insight as to what we would expect. And these are some recent papers looking at precipitation over the Southern Ocean at Macquarie Island and McMurdo Station, so high latitude sites. And these plots, I won't go into too much detail, but when you see green, these are frequency of occurrence of precipitation rates. And what you can see is these are really low precipitation rates, and the green points are really small particles. So this is indicating you get really, really light precipitation in these regions. And we also know that at McMurdo Station, there's a recent paper highlighting that there's persistent supercooled drizzle at temperatures even below negative 25 degrees Celsius. So I think what's happening is from CAM5, we had this temperature-dependent immersion freezing of cloud droplets described by this big 1953 scheme, which was an overactive ice nucleation scheme. So we ended up having a lot of ice crystals in these clouds that would then reduce their cloud lifetime. This is what resulted in those large shortwave cloud feedback biases. In CAM6, we have fixed this, where now we have, even with HUZA, we do have this lower amounts of emergent freezing occurring in the Southern Ocean clouds. However, those cloud droplets are able to persist and grow large enough to become rain. And now this is transferred into the rain hydrometeor type in the microphysics, which gets treated with our big 1953 scheme, which we know is overactive. So this reduction in heterogeneous ice nucleation of cloud droplets is a good move, but this results in supercooled rain production, which is not possible to maintain in CAM6 microphysics. So to summarize, we have a new available emergent freezing or heterogeneous freezing scheme that includes the dust and marine IMP sources. We've added number tendencies into the MG3 or PUMA's scheme, and we are not seeing sensitivities to ice nucleation, which is consistent with previous work using the same model. And again, I'm just highlighting that these other two ice production processes are really dominating the ice production process of the Southern Ocean, and I think this is unrealistic, and it masks our sensitivities to important aerosol ice interactions. And I don't know how much time I have, Julio, because a lot's happened, but I just want to say that this is really important, right? So she was also talking about this cloud phase feedback, right? So in CAM5, we had a lot of ice, and then so that allowed for this really strong cooling effect over the Southern Ocean. Now in CAM6, we have less ice, and at some point, this is a recent paper looking at the equilibrium climate sensitivity and how it's possible based on this state-dependent cloud feedback, where now we have less ice, and after some amount of warming, this ice changes over to cloud water, and this increases the cloud optical depth, which is a cooling effect, so it's a buffer for the climate system. If you look later in a simulation where the clouds have already transferred to being liquid dominated, there's no longer this cloud phase change that can occur to buffer the climate system, right? And so the question is, after some amount of warming, who knows how much, the clouds of the Southern Ocean will become liquid, and then they would dampen that negative cloud feedback. The question is if the model is actually able to handle things like not just changes in warming, but changes in aerosol populations. So we've heard about changes in anthropogenic dust sources. You have glacial melt happening in the Arctic and all over. And if you are not sensitive to these aerosol ice interactions, I think that this could be really important. And so I have a couple, oops, no I don't, because this is an old slide deck, but this is not a finished project. So please provide feedback and questions as you wish. Thanks.
Any questions?
Or comments?
Or comments?
Maybe I'm all wrong.
I wonder if, going back to your picture where you got back to big with the immersion freezing of rain, I wonder if that maps onto cloud cover biases that we have in CAM6 too, because the Southern Ocean is covered with, I mean, it's already a very cloudy place, but it has too much cloud cover when we compare with satellite observations. I wonder if this is consistent with that.
I haven't looked at that, but we should. And the other thing too that was on my future work slide is to look at precipitation rates. We have measurements of that at those stations, and also from ships. I just haven't gotten there yet. But we should be able to see where precipitation should be occurring versus where it is in the model. But I think that this could have a big impact on all things related to clouds.
Well, I guess I'd just kind of follow up on that. I mean, if you're talking about the pathway in CAM6, I mean, it looks like the supercooled liquid comes in the form of freezing rain, and they can't sustain that, so that just becomes snow?
Well, in the model, the rain can become ice or snow. In reality, I think probably what's happening is the auto conversion, and maybe Andrew has comments on this too, but so this idea that cloud and rain are separate is a function of modeling, right? That's not something that's in real life. And so where that division occurs is probably very important, because if you have just really large drizzle drops, where would that fall? Is that a large cloud droplet, or is that a small rain droplet? And how would the physics treat it? Should it be different, et cetera? And so there's a couple ideas of like scaling big to make it less active. I've tried that, it doesn't seem to be the full fix. So the other thing that we need to look at is the rain budget. So how is rain getting formed in the model, does it make sense, and is it consistent? Because there's also a lot of rain throughout the column, which, as you saw from that picture, it's not raining all over the entire atmosphere column.
I'll talk about fixing that tomorrow.
Great.
Once it's rain, why is it a problem for cloud processes? Once it's been sort of shunted into the precipitation box, isn't it out of the cloud radiation system?
Yes, okay, great question.
No.
Well, it is out of the radiation system. It doesn't affect the radiation,
Okay.
but it affects what's left in the cloud.
Yes, so I think the reason why this hasn't been a worry up to this point is because we had a really active cloud droplet activation or nucleation. And so droplets weren't able to get to a super cold state and large enough to be a rain droplet. And so the physics never really saw a scenario where you have very little ice formed, and so you have these large super cold droplets. I don't think that was very common in the model previous to the changes to the ice
You don't
nucleation
want more
scheme.
super cooled rain in the model.
Right, we don't.
You want it over the Southern Ocean. You might have a problem at McMurdo. You don't want it in Boulder. You don't want it over land. The reason big is there is because it's not designed for the edge cases that
That's right.
Christina was talking about.
And so we didn't see it over Southern Ocean before because it didn't, yeah. And so, big, I looked it up, it's in my office, I have a hard copy, and one precipitation sample went into that parameterization, so.
Thanks.
Hey, one data point, you're perfect.
Running late, of course.
No uncertainty, right? Yeah.
So our next talk is from Dave Mitchell, who is remote. Dave, can you hear us?
Yes, can you hear me?
Yes.
Okay, good. Can you see the presentation okay?
We can. It's not in it's not in slideshow mode.
Okay. Can you? We're trying to figure out here. Okay. How about now?
Yes.
Okay, good. Thank you. So this is a talk with Anne Garnier at NASA, or SSAI. We've been working on a new retrieval of cirrus clouds over the last year and a half. And in this talk, I'll just be showing the results. You can see in the picture here, there's two different types of cirrus, and that's basically what I'll be talking about. One is formed by a wave cloud, which is involving homogeneous ice nucleation, and the other isn't. So since I talked about this last year for the methodology, I'm just going to be talking about results this time. But a few things can be mentioned: that we're only sampling single layer clouds that are semi-transparent to the Calliope LiDAR. Most clouds are having an optical depth less than 3. The retrieved cloud properties correspond to cloud layers and not in-cloud profiles. So we're not profiling with a LiDAR in a single cloud. And 4, the sampled clouds have a radiative temperature less than 235 Kelvin. Of course, and the following analysis is based on 4 years of data. So this is a plot for 4 years, looking at 2 different quantities. One is called the integrated attenuated backscatter, and the other is the infrared cloud optical depth. And it's for 6 different latitude zones. And basically it's showing that the integrated attenuated backscatter is about 0.01 when the optical depth is around 0.3. And when it's less than 0.3, our retrievals are not valid over land, but they're valid over ocean. There's a lot more scatter and uncertainty when the optical depth is less than 0.3. So our lowest levels of uncertainty correspond to optical depth greater than 3, or IAB greater than 0.01 steradians. So the retrievals are grouped into 2 categories based on this IAB threshold, or integrated attenuated backscatter threshold. So the next plot is showing the comparison with Martina Kramer's climatology of cirrus clouds all around the world. And the only two things that are actually measured by the aircraft probes are the number, concentration, and the ice water content. This volume radius on the upper left is basically the ratio of ice water content divided by number concentration with a few constants thrown in there. So we're agreeing fairly well, a little bit lower with our RV values. And there's two different basic colors to keep in mind. One is the red and one is the dark blue. The other colors are for the tropics. So the climatology data is the black, and the percentiles are shown by the darker shading is 25 to 75%. So the agreement is fairly reasonable with the number concentration within the 25 percentile for the dark blue. So that's for mid-latitudes and tropics. And the red is corresponding to thicker cirrus clouds that have an optical depth greater than 0.3, or so the blue corresponds, and the red is for the higher than 0.3. So that gives us this question: are there two types of cirrus clouds? You know, for the ice water content on the right, the red curve corresponds very well with the Schilling measurements, which are not shown here. The Kramer measurements are in black, and our total optical depth range is agreeing well with that. Basically all samples that we could measure. So looking at these two measurement categories of cirrus, we can say that the samples with an IAB more than 0.01 represent 28 to 48% of all the samples. So this is looking at occurrence frequencies of cirrus having the lowest uncertainty. And that second, the bottom is showing this, how these thicker cirrus clouds are weighted. You can weight them by occurrence frequency, basically, or the number of pixels counted, which serves as a proxy for the cloud coverage or the occurrence frequency, times the optical depth. So the optical depth is the radiative weighting of these curves. And we compared this with Hong and Liu's paper that was explicitly looking at the net cloud radiative effect, CRE. And when we approximate it by pixel count times optical depth, the CRE we approximate that way, we get good agreement with the Hong and Liu study. So we think it's a reasonable way to do this. So if you do it that way, you get 76 to 88% of the net cloud radiative effect for all cirrus clouds appears to be associated with an IAB greater than 0.01 or an optical depth, visible optical depth greater than 0.3. So the radiative weighting is a lot different than the frequency of occurrence weighting for these clouds. So here's what we retrieved for the IAB less than 0.01. And you can see for number concentration, the concentrations are relatively low. These are basically less than 20 per liter for all the different latitude zones here for summer and winter. This is on the left is tropics, mid latitudes in the middle, high latitudes on the right side. And then the same kind of thing is shown for effective diameter on the right. What we're looking at, I forgot to explain, is the TR minus T top. That's related to the cloud geometric thickness, because TR is most of the time near the middle of the cloud. So the temperature, subtracting the temperature of cloud top from that gives you a qualitative measure of cloud depth, a geometrical thickness. So as you go from, you know, left to right on the x-axis, you're getting thicker clouds. So going now to the thicker clouds, the IAB greater than 0.01, or optical depth more than 0.3, number concentration is a lot higher when the clouds are thinner. So this TR minus T top difference, when it's relatively small or the clouds are thinner, we're having a high concentration of ice crystals, which corresponds to homogeneous ice nucleation at 550 per liter or more. That's got to be homogeneous. And the effective diameters are looking kind of similar as they did for the other category. Now, if we go to ice water content, we see for the thinner cirrus clouds, IAB less than 0.01, the ice water content is a lot less. And like number of counts are given on the right side. So the frequency of occurrence is for thinner clouds. They tend to be thinner in this category. Now, if we switch to IAB more than 0.01, we see the ice water content for the thinner clouds is a lot higher, corresponding to homogeneous ice nucleation. That's where the number concentrations were also a lot higher in this thinner cloud region. And across the board, it's higher ice water content, which you'd expect, of course, for optically thicker cloud. The number of counts are distributed differently now that the clouds are basically thicker than they were before in the IAB less than 0.01. So we have these two attributes now for homogeneous ice nucleation. When N is relatively high, we have relatively high ice water content, and DE tends to be smaller. So therefore, we can distinguish between these two types of cirrus using as a diagnosis for homogeneous ice nucleation. We can use the extinction efficiency, the coefficient shown here for visible extinction. So it's basically ice water content over effective diameter. We're using that as a metric for distinguishing when homogeneous ice nucleation occurs. So here in these plots for tropics, mid-latitudes, and high latitudes, winter and summer, we're looking at the number concentration as it's distributed by extinction. So temperature, radiative temperature on the y-axis, extinction on the x-axis for all of these plots. And you can see something that looks like the Pacific Ocean out here. You know, it's kind of light blue. That's less than 20 per liter. So that would correspond to heterogeneous ice nucleation. And then around the middle of the plot, you get this gradient building up. And we believe that gradient is due to ever increasing contributions from homogeneous ice nucleation. So to test that idea, we invoke the Clausius-Clapeyron equation here. And we use that to get the vapor density at ice saturation. And we also use that Clausius-Clapeyron equation rewritten a little differently here to get the freezing vapor density where homogeneous ice nucleation activates. So the difference between these two, you get a vapor pressure corresponding to activation of homogeneous nucleation, a vapor pressure for ice, at saturation. The difference between the vapor densities gives you the ice water content corresponding to homogeneous ice nucleation. So a very simple model here. The other thing that we add to the model is some kind of empirical relationship between the mean dimension of the size distribution versus temperature. This is shown for Spartacus data, but we also did this for CPEX data in the tropical Western Pacific. And the two relationships were similar. Another thing that we do in this simple model is we tweak that for temperatures colder than 235 Kelvin, we reduce the effective diameter that we get from this relationship by a factor of 0.636. And that's due to the impact of homogeneous ice nucleation that's shown in this next slide. Here on the left side, we see number concentration plots like we saw earlier. And on the right side, we see effective diameter plots, TR versus extinction. And you can see where the red is that homogeneous ice nucleation is very active. And that corresponds to on the effective diameter, where you go from light green to dark blue, and that's due to homogeneous ice nucleation. So the change from 55 microns to 35 microns in effective size is a ratio of 0.636. Another thing is that the end plots here, the number concentrations, show that the IAB of 0.01 roughly separates these two types of cirrus clouds. So we were kind of lucky in a way that we chose this IAB the way we did. It was based on uncertainty of our samples, but it also seems to correspond to something mechanistic in the threshold for homogeneous nucleation. So these are the results of what we found. The triangles are predicted by our simple model superimposed on the satellite results. And you can see for number concentration in the upper left quadrant that the colors inside the triangles, those correspond to the model values. So those are predicted values. And then the satellite pixels are retrieved values. So it's making sense to us because in the mid latitudes and the high latitudes in particular, we're on the boundary, the right-hand side boundary of our samples. And on the lower left quadrant is the frequency or the number counts. So kind of like the frequency of occurrence. And you can see the black triangles from our model correspond to low frequencies of occurrence or lower number of counts. So that's what we also expect from homogeneous ice nucleation, that it occurs only sporadically, very rarely actually do you get these events, but you do get them once in a while, and that's what this is showing. So over on the right-hand quadrant, upper quadrant is effective diameter. The red is not to be trusted, basically. That's where we are not, the retrieval's not sensitive there. But elsewhere, you can see that the colors of the triangles correspond to the satellite retrievals kind of remarkably well, I would say anyway. And then same with the ice water content here. The colors of the triangles correspond to the satellite colors that are just adjacent to them. And that's pretty much true of the tropics, the mid-latitudes, and the high latitudes. So to conclude, the cirrus clouds having an IAB more than 0.01 or optical depth more than 0.3 roughly account for 80% of the net radiative effect of the cirrus clouds in our estimation. But their frequency of occurrence comprises 28 to 48% depending on latitude for all cirrus clouds. Number two, these are optically thicker cirrus clouds. Ice nucleation by both heterogeneous and homogeneous ice nucleation occurs, while only heterogeneous is important for the optically thinner clouds. And based on this number concentration gradient and the extinction analysis, the transition between these two types of cirrus clouds arguably occurs around 55 per liter. You know, you can quibble about that number, but it's somewhere in that ballpark. And number three, the aircraft in situ measurements are critical for testing the satellite retrieval methods, but the existence of these two cirrus modes complicates these comparisons. So you don't really know what type of cloud the aircraft was sampling, and it tends to be the thinner cirrus type. So to get a good balance in your climate models, so that's why I wrote, in addition, the satellite measurements can estimate the radiative importance of each cirrus mode, which should be consistent with GCM predictions of cirrus clouds. So the in situ measurements are helpful, but they may not give you that, that balance of radiative contribution of each cirrus cloud mode. So this seems to be something that could be worked on in the future to improve the models. So thank you for your attention.
Are there any questions for Dave? in the room?
I have a question maybe.
Yeah,
Are
Simone.
those-
Uh-huh.
I mean, if I understand the changes you made, is this something that will be integrated in the model or what's the plan?
Yeah, we do have a plan to try to put this, to kind of hardwire this into CAM 5 or CAM 6, probably CAM 6, where we have a subroutine that contains effective diameters that we retrieved. And that would basically take the place of the CAM 6 predicted effective diameter. And then you can calculate from the model ice water content and the slope of the distribution based on that effective diameter, you can get number concentration predicted from that. So we did this in an ACPD paper in 2020. It's a publication back then, but we found a bug in the model, unfortunately, so it never went to full publication. So we're going to try that again, basically, and with these new retrievals.
Well, thanks, Dave. I think since we're already almost 10 minutes into our break time, we'll call it here. And why don't we take a 10-minute break, more or less come back at 3:35. All right, well, just give people one more minute to take their seats, okay?
Sure, just tell me when to go. I can no longer see you guys with it in full screen.
Sorry, I was trying to pick the most inconvenient seat. My fault.
Why don't you go ahead, Marissa?
Super. Yeah, so I'm here to talk to you about SLIM, which is a very simplified land model that exists within CESM. And in part, this presentation is just to get this land model on your radar, on the wider atmospheric modeling community's radar, if you're not already aware of it. And then also in part to get a little bit of feedback of it that could use some help from the atmosphere side of things, whereas during its development, we worked much more closely with the land modeling community part of CESM. So first off, there's sort of an obvious question. We have CLM, the community land model, which is a fantastic, very complex land surface model. So why did we want a simpler model in the first place? And there were a few reasons that really prompted us to go down this pathway. And mostly it was that we really wanted to identify where the atmosphere was most sensitive to changes in the land surface and to understand what surface properties matter the most at any given location, to really untangle the physical pathways through which the land can influence the atmosphere. And this can be very difficult to do in a complex atmospheric model, which I will walk through in just a few minutes. So it's pretty intuitive to think about how the state of the atmosphere impacts the land surface, and the vegetation growing on the land surface is going to care a lot about things like how sunny it is and how much water there is, the temperature, and so on. But it's really the two-directional coupling of this that we wanted to dig into with this idealized land surface model, and that's the idea that changes in the land surface can actually drive responses in the atmosphere. And this was very much motivated from a sort of biogeophysics point of view, so not really thinking about carbon or nutrient cycling. And the idea here is that if you have a change in the land surface, like changing from bare ground to a grass to a forest, that's going to change a lot of physical properties of the land surface in a way that changes your energy fluxes and water fluxes to the atmosphere. And that can drive local atmospheric responses, which can then feed back on the land surface, and it can also drive very large scale global atmospheric responses. And the point here is really that it's just a coupled system. So the atmosphere is influencing the land, but the land is also influencing the atmosphere on a variety of scales. And these changes in vegetation, they've been shown in various modeling studies, including with using CLM, to have very big impacts on the overlying atmosphere. But it can be really difficult using these complex land surface models to understand exactly why some change in vegetation drives an observed change in the atmosphere. So as a little case study here, we can consider converting a grassland to a forest, and this involves several biophysical modifications of the surface at the same time. So for instance, you're going to change the albedo of the land surface, which is a function of the leaf area and the color of the leaves. So it's something that the model figures out for itself based on sort of how happy the plants are and what plant is growing there. It's going to change how hard it is to get water out of the plant and up into the atmosphere as a function, again, of leaf area as well as stomatal properties, so really physiological properties of the vegetation itself. It's going to change aerodynamic properties of the land surface, often parameterized as a function of vegetation height. It's going to change how hard it is to get water out of the soil and into the plant and therefore up to the atmosphere, and generally just the water use and available water that is left in the soil based on how quickly the plants are using it. So what this means is that if you do an experiment like this in a model like CLM within CESM, and you change a chunk of grassland into a chunk of forest, and then you get a really interesting atmospheric response, like a change in cloud cover, for instance, it can be very difficult to understand why that atmospheric response is occurring, because all of these changes happened at the same time. And there are multiple changes to the land surface that you might expect to drive the change in this case, this little dummy example, cloud cover. And you can't always tease apart which one it is. So for instance, you made the surface darker and perhaps warmer. You also perhaps changed the turbulent mixing, and you changed how much water you were putting up into the atmosphere, all of which you might expect to influence processes within the atmosphere. So what we really wanted to be able to do was to be able to directly control each of these surface properties. And that's actually very difficult to do in a complex land surface model like CLM, because many of these properties are either dependent on one another. So if you change one of them, you will necessarily change the others or just break stuff, or because they're emergent properties of the model. So albedo, I mentioned, is a good example of that, where it's actually very difficult to tell CLM what the albedo of the land surface should be, because it's going to figure it out on its own based on how well it can grow its vegetation. So that's what prompted us to develop this idealized land surface model that we're calling SLIM. And what is in the land surface model is basically just what is shown in this cartoon. So it is a very, very simplified land surface model. It looks a lot like the early land surface models of, the 60s, 70s, 80s. So we're not reinventing anything here. We're just going back several decades. But what it really represents is just a temperature profile in the soil column, and then you could prescribe the aerodynamic roughness of the surface, the bare ground albedo. There's a very simple snow model that masks out the albedo of the land surface. The snow can melt into a bucket. Hydrology is just represented by a bucket. So if you want to evaporate water to the atmosphere, it is parameterized as a function of how full your bucket is, as well as sort of a resistance you can think of as associated with a lid, or if you're thinking in terms of the actual land surface, this would have to do with things like soil properties or vegetation or stomata. And this is really all that is in the model. So it's very, very simplified, but it sits where CLM usually sits within the context of CESM. So it's sort of borrowing the coupling infrastructure from CLM, and then it can couple with CAM. Typically, we run it with the slab ocean and the sea ice model. But what this lets us do is really control directly these tunable knobs individually. So we can tell at the land surface what the bare ground albedo is, independent of the rest of these properties. And we can put albedo back and tell it what our change in roughness should be, and so on in terms of evaporative resistance and how much water the land can store, and how much snow you should put on the land surface before you mask out the bare ground albedo, and then the sort of thermodynamic properties of the soil. So those are all of the parameters you can tune within the land surface model, and you can directly change those parameters, which means that you can know exactly what change you have imposed on the land surface, and therefore know what the atmosphere is responding to when we do these kinds of simulations. So just for a sort of quick, not too in-depth on the science, but quick little cursory example of some of the things that we've used this idealized land surface model so far are things like sensitivity tests. So seeing how the atmosphere responds to changes in different land surface parameters. And on the left, what you're seeing is the pattern of a global decrease in land surface albedo. And the colors are showing you the change in temperature. So you see that the same change in land surface albedo does not give you the same change in temperature everywhere. And on the right, the figure is showing you the same thing, the change in temperature, but for making it harder to evaporate water from the surface. So as you increase the evaporative resistance, that means you get less latent heat flux and you get warming. But again, the pattern of this warming is very spatially heterogeneous. And that's the sort of thing we can do with this idealized land surface model that would be difficult to separate in a model like CESM, or like CLM rather. And this is using SLIM, but coupled to CAM again and a slab ocean. Wen Kong, she was a postdoc at UCLA working with Karen McKinnon and Isla Simpson. She used a similar set of experiments where she changed how hard it was to evaporate water from the land surface to explore impacts on temperature extremes and variability. So she was using a much more realistic setup of this idealized land surface model. You can make it look pretty much like CLM if you put the same properties in that result in a CLM-like albedo, and then you can start tweaking them to see what it does to things like variability and extremes of your temperatures in this case. It's also pretty easy to override certain values in the model. So what you're seeing here is two simulations, one where we allowed the soil moisture to freely evolve coupled with the model, that's in the top, and then the bottom one where we prescribed climatological soil moisture. And you can not really worry about the line graph, but the pattern on the right is just showing you the first mode of variability of 2-meter temperature. And you can see that that pattern is very different if you allow soil moisture to interact, like the top one, whereas if you just prescribe climatological soil moisture, you get a very different pattern. And that's, again, something that is fairly straightforward to do in this very simplified land model. You can also do some much more sort of out there experiments that help us learn things about the land system, but are a little less perhaps applicable. So for instance, you can make all of the land look like a desert just by making the bucket tiny and making it impossible to evaporate water. And you can compare that to what the world would look like if all of the land looked like a swamp all the time, just by forcing the bucket to always have as much water as it wants. And what you see in that case, this is just showing you the difference between the desert land and the swampland simulation, is that you do indeed get less evaporation from your desert land, but you actually end up with a planet that is significantly more moist. It has more water vapor, and that's just because the residence time of the water vapor goes up by several days because the planet as a whole is considerably warmer. So the reason that we're presenting this sort of talk about a land model at the Atmospheric Model Working Group is really for two reasons. Like I said, just to get it on your radar if it's not something you're already aware of, and also to get some feedback from the Atmospheric Model Working Group community for some things that CAM needs from SLIM, or needs from a land model that SLIM can't produce. So we knew about the dust, and we get around that pretty easily just by prescribing a climatological dust flux that SLIM passes up to the atmospheric model. That's easy. We spoke with some of the Atmospheric Model Working Group members late in the fall, and what came up was that we need some way to deal with dry deposition of aerosols. So if there's anything else like that that we've missed that we should be addressing, we would obviously like to address it sooner rather than later. Because SLIM is going to be sort of looped into the regular CESM releases in the very near future. So it's going to be included in the CESM 2.3 release. This is thanks to a great deal of effort from Eric Kluzek and Sam Levis, who are much better at coding than I am and are cleaning it up in a way that makes it much easier for everyone to use. So you'll be able to toggle SLIM on and off just like you do with CLM, where you would build rather than using CLM, you'd build with SLIM. You can already use the model though, if you're interested. It's sitting in the ESComp GitHub repo. You just can't sort of build CLM and SLIM at the same code base right now. So again, if you have any questions, comments, concerns, why on earth have you replaced CLM with this bucket, please reach out to me. I'm all ears. We want to make it a useful tool for the community. That's it.
Are there any questions in the room? Colin and then Isla?
Yeah, so very, very nice talk. A bit of a naive question, I guess. So just thinking as far as where we could use this in CAM development, you know, one issue we've been having with the boundary layer parameterization has been these oscillatory behaviors that we think in some way, shape, or form are tied to surface roughness or surface drag over land. Is it pretty trivial? I mean, how are these variables specified? Is it just kind of like a flat netcdf file, and if we wanted to modulate something, it's as simple as changing the aerodynamic roughness over a given patch?
Yep, that's exactly it. So you feed in a netcdf file. It has sort of 12 months, so you can make it vary seasonally, and for each month it has a set of parameters, and you just tell it, what should your bare ground albedo be? How much snow do you need to mask the albedo? How aerodynamically rough should it be? And that's just really the, like, literally the roughness that goes into the Mononobikov parameterization. And yeah, you just change that number and run the model off that netcdf file. So it's very, yeah, it's not fancy, but that's the point.
Something to play with. Thank you.
Yeah.
I was just wondering if there are any further thoughts on how to deal with the dry deposition issue.
Yeah, so I dug into this a bit after our conversation in the early winter, and was surprised how little it was seemed to be affecting stuff, but it definitely is when I like go and look at the actual dry deposition fields. Like there is a definite, you know, trend in those values in the runs where it can't get stuff from CLM. I have not figured out how on earth CLM is giving it any information about dry deposition, but it sounded like from the CAM people, maybe it's not, and like CAM's getting it. So I need to figure out how CAM gets its dry deposition information. I think Eric had some ideas on that, and we just need to reconnect and dig a little deeper. So that's a really long-winded answer to say, I haven't forgotten about it, but no.
Hi, that was a very nice presentation. I think it's going to be very useful for the community. I just wanted to ask if you're, or maybe ensure that you've been talking to the Paleo Climate Working Group, because I think the Paleo group would really benefit from using something like this in terms of sensitivity, in terms of, you know, changing worlds and different geographies and, like, I personally have done experiments where I've made desert everywhere, but in a complicated CLM sense, this might be easier to do it with the SLIM. So I just wanted to make sure you guys were, because there may be, someone in the paleoclimate community might actually have some further suggestions for you.
Yeah, that's a great idea. It's definitely been, it was one of my motivating sort of drivers of why we might want a model like this is in a long paleo context. We don't even know what vegetation to put in which places. We don't know that that vegetation should behave the way that our modern parameterizations of vegetation do. So that would be a good motivator for it, but I actually haven't given this same talk at the paleo working group, and perhaps I should, because as you say, they may have good suggestions of things we might want to make sure are there in terms of functionality. So thank you.
Great.
So I had a quick, I was a little confused about soil moisture and the bucket. It's
yeah.
You could fix the bucket to, have a certain amount of water all the time. Is the bucket the same as soil moisture in SLIM?
The bucket is the soil moisture. So the bucket, you could effectively say how big your bucket is. And if you're letting the bucket interact like a normal version of SLIM, you would rain water into the bucket or snow onto the surface, and the snow would melt into the bucket, and the bucket would fill up. And if the bucket got too full, it would go into runoff. And if you wanted to evaporate water from the land surface, there would be some resistance, and it would take that water out of the bucket. And it would all be dynamically interacting. And the bucket depth is just sort of how much water you can store. So you can say, oh, this soil really can't store very much water. Let's make the bucket really small. Or this soil should be able to store lots of water. Let's make the bucket really big. But it's the simulations I showed where we fixed the soil moisture. That's sort of a special case, which is just to show that it isn't that hard to do that. If you wanted to, you can override within the SLIM code what the interactive soil moisture I say, which is water in the bucket, would be just by feeding it in through that input netcdf file and saying, ignore what you think soil moisture should be, make it climatological soil moisture instead. And it's just, numerically, it's fairly straightforward to do.
Thank you. Oh, thanks very much. I think unless there are any other quick questions, I think we'll move on. Thank you.
Great, thanks.
Next talk by Meg Fowler.
Okay.
So take it away.
Okay. Awesome. Okay. Well, thanks for. Meg Fowler. I'm a project scientist here at NCAR and CGD. And today I'm going to talk a little bit about ways we've been looking at how to enhance the ability of the atmosphere to respond to subgrids. Okay, that's, no? Okay. Like, yeah, just making sure everyone's awake. Good, okay, perfect. Yes, so I'm gonna talk about land surface heterogeneity. I do realize that in the session before, heterogeneity and homogeneity were used in a completely different way, so sorry about that. I mean from the land surface perspective. So when we think about the ways in which the land and the atmosphere interact, what I find really interesting is that even small scale differences in surface cover and surface type drive really important impacts on the atmosphere. So you can imagine a situation like the picture here, where in the real world you'd have cropland next to a forest and a grassland in an urban area. And all of those differences in roughness length, in temperature and moisture, ultimately can impact where boundary layer cumulus clouds form, precipitation, things like that. The main way that this happens is really through the generation of mesoscale circulations. So when you have these gradients in temperature and moisture, the atmosphere wants to equilibrate those to some kind of constant. And so it sets up this overturning circulation to try and get there. What's interesting is that even though this happens at kind of a small scale, so on the order of maybe a few to tens of kilometers, you might have these surface gradients, the impact can kind of extend upwards of 100 kilometers. So at a grid scale level, you can see it impacting things like liquid water path and turbulent kinetic energy. Now, as most of you probably know, land atmosphere, sorry, there's a picture that did not show up. Well, okay. land atmosphere coupling in global climate models is really relying on grid mean fluxes right now. So even though we might have this information on surface heterogeneity within the land model, when the atmosphere is communicating with the land model, the only thing that's being passed is a grid mean flux. So from an atmospheric perspective, you have a homogeneous surface underneath an atmospheric column. What we'd like to see is something a little bit more realistic. And so this is part of a climate process team that's been ongoing for a few years called CLASP. CLASP stands for the Coupling of Land and Atmospheric Subgrid Parameterizations. It's a multi-institutional effort. There's a lot of people involved, but ultimately the goal is to move from the picture on the right to something more like the picture on the left. And it's really a good time to start thinking about how to do this because both the land and the atmospheric model already contain representations of subgrid scale heterogeneity. So in the land model, the way this works is through a tiling scheme. So within a given grid cell, you can have vegetation, lake, urban areas. You can have different crop types, whether they're irrigated or unirrigated, and you can have different vegetation types, so trees, C3, C4 grasses, and things like that. Now the way this actually works in practice is you break down a grid cell based on the area that's covered by a certain surface type. So you can imagine a situation where this sort of idealized grid cell is made up of 50% irrigated crop, 30% forest, and 20% urban area. Now the interesting thing is that although we have the percentage of the grid cell that's covered by each surface type, we don't know anything about how contiguous that surface is. So it's equally possible that the irrigated cropland is scattered around the urban area, maybe of 3 cities. So just to note, I'm showing you the idealized version, and I'll keep doing that, but don't take that as a literal interpretation. On the atmospheric side, there are also representations of subgrid heterogeneity. So CLUB, I think we've heard a lot about kind of off and on. I won't get into the details. What I do want to highlight is that CLUB predicts the variance and covariance of temperature and moisture at the surface. And so you can kind of imagine if you have those 3 different surface types, they all have unique surface fluxes, we could probably get some idea of what the actual surface variance is in temperature and moisture. What I want to highlight for today's talk, though, is that there's an ongoing CPT as well for CLUB MF. So MF stands for a mass flux. So if you think of kind of the eddy diffusivity, that's CLUB's job. Mass flux is really to have a bit more of an organized approach. And so it has these multiple updraft plumes within a grid cell. So in this case, I've just put 10 updrafts. And you can imagine them just lofting temperature and moisture into the vertical. So not only do we have CLUB, we have this additional source of subgrid heterogeneity moving forward as well. The question is really how can we link that subgrid information together? The land model and the atmospheric model both have their estimates, and can we make them talk to each other? So from the atmospheric side, with CLUB MF, we can imagine that the surface plumes are over pretty much a homogeneous surface again. So the atmosphere, each of the plumes is forced by a grid mean sensible and latent heat flux, grid mean temperature. But we could, in theory, move to something a little bit more realistic. So if we know that a grid cell is made up of 50% irrigated crops, then we should initiate 50% of our plumes with the surface fluxes that are indicative of that particular surface type. Similarly, you could sort of break these down into each surface type within a grid cell. Again, this is idealized, sort of works out perfectly with the percentages that I gave it, but just as an idea, this is one place to start. So if we did want to initiate plumes over actual subgrid surface patches, the way that we do this is we pass surface patch level data through the coupler to CAM. This is a little bit easier now that we have CMEPs. It's actually not too hard to do. And then we would initiate these mass flux plumes over each individual surface patch given the area within a grid cell. That'll replace the grid mean latent heat flux, sensible heat flux, and surface temperature with those patch level values. So for our initial testing, we're using single column SCAM ensembles. These are at the Arms of the Great Plains site. There's been a lot of work at that site historically. And I'm going to show you some initial results from 74 warm season shallow convection days. This is sort of a carry-on from other parts of the class project, which I won't get into. But we're looking at 2-day hindcasts using the second day for analysis, so the model gets a chance to spin up. I'm going to show you an average over all 74 days. I'm also going to caution you, these are very preliminary results. So purely illustrative, don't take this as absolutely what's going to happen. So I'll explain in a minute. So what you're looking at here are the plume updrafts for CLUB MF. So this is the updraft temperature within each of the 10 ensemble plumes. On the top is the CLUB MF implementation, so sort of default, turn on the mass flux option. And then on the bottom is where I've modified it so that each plume basically is being initialized over the surface type where it, in theory, resides. What I think is important to note here is that along the bottom, the variance within plume temperature is increased quite a bit. That's probably a good sign. Now that they're being initialized over unique surfaces, you should see more variability in the updraft temperatures. That said, here at 3 p.m. local time, so this is an average over those 74 days at 3 p.m. in ClubMF and in CLASP, so sort of our heterogeneous version, probably shouldn't be seeing 40 to 50 Kelvin spread down at 925 hectopascals or so. So again, take it with a grain of salt. This isn't quite worked out the way we want it to be, but there is an increase in variance, so that part's good. Really what I want to highlight today is just that I think this gives us a lot of opportunities to develop the model further. So the way that I've sort of implemented this just as a first pass is let's just allocate the updraft plumes based on the area of the surfaces within the grid cell. But there's other work that's been done. So Khalid Ghanem is out at Princeton GFDL, and he's part of CLASP, and what he's done is looked at EDMF schemes, how you can add in surface heterogeneity. And his findings suggest that if you alter the updraft area and the updraft vertical velocity, you can really start seeing important atmospheric impacts from having that surface heterogeneity present. So I think that's something that we could explore moving forward as well. What I think is also interesting is maybe some options to communicate information back to the land models, that it's not just a one-way communication of heterogeneity. If we have these updraft plumes and in some sense can kind of allocate them over different surface types, maybe we can start to investigate ways to pass information back down to the land model. There's cloud cover over the forest, there's precipitation over the urban area, and things like that. So still needs a lot of development, but I think it's worth starting to think about how we can do this more robustly moving forward. So obviously there's a lot of development still needed. These results are very preliminary, but I think there's a promise now for moving beyond treating the surface as a homogeneous layer for the atmosphere itself. So thanks.
On the horizontal axis on your mass flux plot, that's not temperature, because it doesn't go to 0.
Yeah, it's
700 millibars.
No, that's a good point.
Which plot?
All of them.
All of them.
What's the
So
horizontal
up here
axis?
coming up to 0. I'm wondering
Is it mass
about.
flux? No.
It's
Like-
updraft theta L supposedly.
Is it
But-
variances of temperature?
I don't know the
It
actual.
might be the variance.
Yeah, I think it might.
Even that would be the square of the variance, I don't know.
Yeah.
The problem is that this is a manifestation of how we output the history when you add a dimension, the dimension in this case being number, ensemble member. And the fact that we subcycle clubs 6 times in a time step. And so what this actually is the mean updraft over all 6 of those time steps. Sometimes that updraft may not have launched, sometimes it may have launched high. And so taking the time average over those 6 substeps is, you can't do it without setting where it's not active to missing values before you do the average. It's a problem with the history output, and we should talk about that.
That's good to know.
So you're saying this is a consequence of averaging in zeros where there is no updraft?
Right, where there is no plume, it wouldn't have a temperature, it would just set the temperature to 0, it should be a missing value. But,
So this could just mean plumes never made it to
Does that, which
900
makes sense?
millibar?
yeah.
Okay.
Exactly.
So don't trust it about when it's 0.
0 temperature doesn't look good.
And that's a good point, the huge spread may be the result of this averaging the history tape as opposed to an actual bug, so I'm glad that, Andrew, you brought that up.
Maybe you said this, Nate, but do we know that the spread in the top level there is underestimated in terms of, is that the feeling that it should be wider than, maybe you mentioned this?
Yeah, I haven't compared it to like LES to see kind of what we should expect in LES or in observations. But I think that's something that we probably want to do moving forward, just so we know. Yeah.
This might be too in the weeds, but when you're bringing in the code, when you're bringing the patch information up, does that mean, are you basically just adding a new dimension to kind of the cam in?
Right.
structure?
Yes.
That's the patch, oh, okay.
Yeah.
Cool, that was it, all right, thanks.
Great question, thank you.
No problem.
Thanks, Jesse. Yeah, you're just basically, and it's not, implemented perfectly. Ideally, I would know ahead of time how many patches there are, and then just pass exactly that. I've kind of kludged it in with like 99. There shouldn't be more than 99 surface types within a grid cell. And so it just sort of fills in accordingly.
Could you get that info from CLM? Like, would CLM tell you how many patches there are?
You can, but not at the first time step, which is kind of problematic. So like the way that CLM initializes, when it starts, it doesn't know how many patches it has before CAM has to start. And so I can't initialize my data, probably. But yes, there's probably a way to do it, and I just need help. So I will talk to you. Yes.
Cool. And I'll tell you, I don't know, but yeah, all right, thanks.
Awesome.
Any thought about, sorry, about using some of this information to parameterize mesoscale organization? So, I mean, you said you can parameterize the plume sizes by surface type, but, if there's a lot of contrast between hot and cold, and it's just, you might actually, that might be what controls plume size, the contrast, not.
Yeah, the gradient in it.
Right.
Yeah, I think that's a really interesting point. I think you're probably right. I think it's the gradient more often than not that really matters. It's not where it's just, oh, it's wet, no, it's dry, it's that transition area. I want to say Paul Dermeyer is doing a little bit of work to look into that relationship, but I don't know offhand how to put it in here, but I think that's worth thinking about.
Yeah, kind of a naive question, I guess. So I can obviously imagine this being a big problem or something that's really important at like 100 kilometer by 100 kilometer grid box where you have a lot of heterogeneity. Are there particular scales where you think the benefit from moving to such a framework would be lessened? Or do you think this is something that, because we heard some talks this morning about 3 kilometer models. Do you continue to think that accounting for this at 3 kilometers would still be important, or is that way far off, or?
Yeah, I mean, it would be, I'd say, less important. I think, obviously the bigger the grid box, the more heterogeneity you're just masking. At 3 kilometers, it might not be huge, but given that we're probably not gonna get to global 3 kilometer models anytime too soon, even at like 25 kilometers, I think you really still wanna be figuring out how to handle that surface heterogeneity.
So you still have a decent number of, even at 25, you still have a decent number of surface types in that column.
Yeah, I think you definitely can, so.
Thanks.
Yeah, somewhere between 25 and 3, probably stop caring.
All right. Were there any questions online? Or?
No.
Okay. All right, well, thanks, Minnie. All right.
Okay.
Our next talk is from Cecile Hanet.
Okay. Okay, then. if you are still there, I assume it's the talk you have been waiting all day long. Then, or maybe you just fell asleep and you didn't wake up in time. But anyway, you are stuck, and it's the last talk. I hope I will be fast. There is a lot of echoing, and I don't know. Maybe I'm too loud. Yeah. Is it okay, Nick? Okay. Even Nick ran away. Wow. Oh no, it's back here. Okay, then I'm going to talk about using a variety of slap ocean model to evaluate the climate sensitivity in CSM. And the motivation in this talk is that the equilibrium climate sensitivity, you obtain this by doing a doubling of CO2, and you look at the change in the surface temperature. And the procedure to do it in CSM is fairly involved. And the motivation was to see if we can simplify the procedure to do this. Then the first thing, to give you a little bit of background, when you estimate the equilibrium climate sensitivity in CSM, you usually do it with a slap ocean model, what we will call the SOM in the rest of this talk. And a SOM, it's basically a mixed layer ocean model where you have a prescribed ocean heat flux, what we will call in this talk the Q flux. And why are we using SOM to do this? It's because you will reach equilibrium after a few decades in SOM, while if you run a couple model, it can take like thousands of years. And this is here an example of typical SOM experiment that we will do with CSM. Then I'm doing here a one-time, then I'm doing a one-time CO2, and I'm doing a instantaneous two-time CO2. And then you see that the one-time CO2, there is no drift in the global surface temperature. I initialize here everything from the couple experiment. And in the two-time CO2, you see that I have reached quasi-equilibrium after about 40 years. And the climate sensitivity, the equilibrium climate sensitivity, we look at the difference here between these two, between the two-time CO2 and the one-time CO2 for the year 40 to 60. And there is other method to compute the climate sensitivity. You can look at Gregory plot, you can do radiative kernel, and we are not going to talk about this at all here. We are just interested in the SOM experiment and this type of experiment that I'm showing here. Then this is the climate sensitivity in 3 versions of CSM, and you see that different versions of CSM have different climate sensitivity. Between CSM1 and CSM2, the climate sensitivity increased by about 1 Kelvin due to cloud feedback. Between CSM2 and what I call CSM3 star, if you didn't know CSM3, which was just released between the two talks, no. CSM star, it's our development version of CSM. It's the CSM L58 with MOM6. And if you look in between CSM2 and CSM3, then it's not that much different. And the green line and the red line are fairly similar. Now, the equilibrium climate sensitivity, it's a global number. It's only one measure of climate sensitivity. And we need to remember that models that agree in terms of the equilibrium climate sensitivity, like CSM2 and CSM3 star, can have very different regional response to increase greenhouse gases. And here I'm just looking at the annual change in the TS when I double the CO2. And this is in CSM2 and this is in CSM3. And here I'm showing the zonal change. And you see that even if the global number are the same, regionally it's quite different. And in CSM3 star, you will see that the change over the Arctic is much stronger, while in the yeah, near the equator, it's much less than. Oops, this thing is doing its own thing. Okay, then this is something to keep in mind. But here we are just looking again, for the purpose of this talk, at this single number. And also a quick word about the CSM1 climate sensitivity. We are aware that in the number that I was showing you before, it's 3-point-air. We are aware that it's different from what was published in Gettelman and al. In 2012. I'm using here a sandbox to do some of my experiment that I borrow from Jesse. And this is the only version of CSM that still work on Cheyenne, as far as I know. Then the sandbox give a little bit different value, and we are aware of it, and it's okay for our purpose. Okay, then this is the procedure that we need to do to estimate the Q flux. Then first we need to have a 50-year well-balanced couple run, and it should be in the same configuration as the sum run that I'm going to do. When I say same configuration, it's the same model version and also the same resolution, the same everything, the same vertical level, the same everything. And then once you have a well-balanced couple run, 50 years, because you want to capture the variability, you can compute the Q flux with this equation. And basically, yeah, this is here the Q flux. And then it will be, you will have the net heat flux into the ocean that will come from the atmosphere and the sea ice, and the change here in temperature that will come from the ocean model, and also the mixed layer depths that will also come from the ocean model. Then the Q flux by construction are periodical. It's a 12-month series, and they are normalized to have a zero, a global annual mean equal to 0. And this is fairly involved because you need first to do this long couple simulation. You have to make sure it's balanced, and then can we get away with something simpler? And it's what we wanted to do this. And here, I'm looking at the Q flux in the 3 versions of CSM that I'm looking, CSM1, CSM2, CSM3. And basically, you could even wonder if I didn't put 3 times the same figure. They look fairly similar. Then the question was, do we really need to do this every time? And we wanted to answer 2 questions here. It's that, do we really need to compute a Q flux for every version of CSM? And also, can we even get wilder, and can we just use an idealized Q flux that would be much simpler than this complicated Q flux? Then this is the 2 type of experiment that I'm going to do. Then to answer the first question, do we really need to compute a Q flux for every model version? And I'm going to run, here I'm going each time to run CSM2. And in one case, I'm swapping the CSM2 and the CSM1 Q flux. I'm going to run CSM2 with the CSM2 Q flux, but also with the CSM1. And the other experiment, can I use idealized Q flux? And we just started by doing a zonal Q flux. Can I wait until, yeah, go ahead.
Does the mixed layer depth also come with the Q fluxes?
Then we have done also this experiment where, okay, in this case, the stuff that I'm going to show here, I'm using the same mixed layer depths, but we have done experiments where we change the mixed layer depth and it doesn't matter that much, but I don't want to solve my, yeah. Okay, then this is what we are doing, but it's a good question, but yeah. Okay, then in the second one, we are using this zonal Q flux, and this is now the result. Then the first experiment, I'm swapping the Q flux CSM2 and CSM1, and you see here, I'm using global value, but if you look at the zonal mean here, they look fairly similar. And then when I swap this Q flux, oh my gosh, I did only the one-time CO2 experiment, and this is the first when I'm not touching the screen, but it's when I'm using the CSM2 Q-flux in blue, and this is as expected. And then when I use the CSM1 Q-flux, I have this major dropping in the surface temperature. Then everything starts in the 60 area, and if you look it will be, oops, oh my gosh. Okay, then it will be really in the region over here at the tip of South America. It's really where it started, and then it propagates everywhere. And I'm not showing plot of this here, but we have started to look at all the surface flux, latent heat flux, sensible heat flux, and you will see this signal and also the sea ice that will grow very quickly. And also, interestingly, then, because everything was happening was starting in this area over here, what we did also, we did other type of experiment. Instead of swapping the CSM1 Q-flux global, we just swap the northern atmosphere, and then I don't see this kind of behavior. Then it really seemed that the southern atmosphere, and in particular the southern ocean, it's really where stuff are really, really important. Then after doing this, I was even wondering, should we even move to the next step? If the model is reacting so strongly between the swap between these two Q-flux, what is it going to do about this? And then interestingly, then this is a completely different story. Then this is the climate sensitivity when I use global Q-flux on zonal Q-flux. Here, twice the Q-flux are coming from CSM2, but in the blue line, it's the zonal Q-flux. This is not the same number, then they're different, but this is not like completely ridiculous number. Then there's still hope that maybe we can try to, for some purpose, try to build a idealized Q-flux. And and here you see that this difference is coming again in the Arctic and also mainly from the southern atmosphere. Okay, then this is something that we have been wanting to do for a long time, because I should say that every week I get an email of people, I want to do the SUM experiment. People want to use all the time the SUM. And then I don't know exactly how to tell them, because we never really try to dig into this to see how much of the detail matter, because they are going to use different version of the model, and does it matter? Then, okay, this is my conclusion. Then we were trying to understand how much of the detail of the Q-flux matter in the assessment of the equilibrium climate sensitivity, and we took this matrix to do this, but it can also be generalized more to some, and we wanted to know if we really need to compute a Q-flux for every version of the model. I'm changing this little thing. If I wanted to use the SUM, do I need to redo a couple model to tune it, to compute the Q-flux? And then can we use also an idealized Q-flux? Then the first set of experiments show that the detail of the Q-flux between model version really matter. And you saw that swapping CSM and CSM1 and CSM2 Q-flux led to a catastrophic cooling of the surface temperature. And it's really the southern hemisphere, and in particular the southern ocean, that matter the most. Now, more work. Here I'm looking at difference between CSM1 and CSM2. This is a big jump. But now if I'm doing like a small change, if I want to do some experiment where I will look at change of parametrization, do I really need to redo the Q-flux? What's the increment that I need? Yeah, which type of increment can I can go away with the Q-flux that I'm using? Then it's really something that we haven't figured out yet. Then we need more work to do. We know that big increment, it doesn't work, but small increment, it can work. And then there is the potential role of the sea ice that's really clear in this experiment. And then we have been exploring an idealized Q-flux, and here we have just used a zonal Q-flux, and it seems promising or at least interesting result. And we are still wondering if there is option to build an idealized Q-flux. And this is all I wanted to show you. Then I put. No, I just add this after. I just had this after Christina talked because I said, oh, she has this cool stuff. Then it's come from a CGD exchange on Minecraft that we had recently.
You need to make a snow version now.
Yeah, it's true. I will, next year.
I have a question. Yeah, I love that you're doing this, first of all. Thank you. So, so for like a paleoclimate world, an equilibrium paleoclimate world, where it's a warm world and there's no sea ice, do you think that your first swapping would actually work? So like you have paleoclimate simulations are really hard to set up. Sometimes you go from one version to the other, and if you had Q-fluxes from like say CSM1, but and there was no sea ice anywhere, could you potentially use those for CSM2?
This is we need really to do a more detailed analysis of really the reason of this collapse.
You should use a paleo world that doesn't have sea ice. Like a
maybe
PTM.
This is the way to go.
Yeah.
But it's a very interesting question. It's really the type of this I cannot tell.
It's super
like this,
interesting.
but it's true that everything is happening.
I think it's
this
very valuable
region.
work, so definitely keep doing it.
Out of curiosity, do you know how frequently that would occur? Like if you tried a different initialization with the CESM1 Q-flux to see if pretty much every atmospheric condition you use, or if you ended up at some weird saddle point?
Then if I was the blue curve, you mean if...
Well, so the red curve, so you get this...
then the blue curve, if I was initializing from whatever, if I would obtain this...
It's just interesting to me looking at like the southern hemisphere Q-fluxes, there's a decent amount of variability there. So it's like you said, it feels like there's something weird going on maybe at the sea ice edge interface that's driving the climate into this regime. I'd be interested to see like, if no matter what you throw at it, it's like, as long as you use that Q-flux and that CESM2 configuration, it's just always gonna get cold. Or if it's just that some combination, I mean, that doesn't really solve your problem.
and it would be, I suspect that it will get cold, whatever the initial condition that I use. But it would be easy to test because it gets cold within like 10 years.
Yeah,
I can
pretty
tell
quickly.
within 10
Yeah.
years or even within 5 years, I can tell if it's... the Wyler and then Andrew.
There's one online, it sounds like, too.
Okay.
We can go for the online one.
Okay, Gian, Ayla, and Andrew. And then we go to the restaurant.
Thank you, Cecile, for the interesting study. So first I want to let people know that I try to run slab ocean simulation of the last glacial maximum. And the simulation usually will run into like a snowball Earth, very cold climate, just like what you showed in your swapping slab Q-flux simulations. And sometimes when I use shorter time step in every component, it helped. And sometimes it didn't. And I went to the code and look at the temperature equation in the slab ocean. And I think it's a simple forward scheme. So I'm wondering whether we can improve the numerics of the slab ocean model that might help to make the model more stable.
Yeah. No, this is good, and it's interesting to hear that you have done the same. You have seen the same time of issue. Yes, thank you. Ayla?
I'll go for the other questions.
We will talk more at the restaurant.
So if the thing's collapsing temperature-wise, it's because there's a total heat capacity in a part of ocean and there's no communication laterally in the slab ocean. So what you're getting is some problem, the surface fluxes aren't in balance with what's happening above it. That can also happen with, if the layer is artificially thin, you'll get a big response. And so I'm wondering if you've looked back at what happens with the mixed layer depth, because there's two things that go into this model. One is the Q-flux map, but the other is the mixed layer depth map.
Yeah, and what I did, I tried to do experiment where I will, prescribe the mixed layer depth. I change it. I use the CSM2 Q flux, but I can change the mixed layer depth.
Right.
And it will not collapse at all as long as I use the CSM2 Q flux.
So you swapped the, yeah.
Yeah, then I use the CSM2 Q flux, then the one that doesn't collapse, then basically the one that, it would be equivalent to this one. Then I would look at this line over here, and then if I use the CSM1 Q flux, it collapses. But at the experiment I was showing here, I was using the CSM1 Q flux and the CSM1 mixed layer depth. But I was trying to figure out what matter, is it the Q flux or is it the mixed layer depth? And I did experiment when I used the CSM2 Q flux, but I used the CSM1 mixed layer depth, and also I divided by 2, and I didn't see this drop of temperature that went crazy. Does it make sense? Yeah.
This is sort of a follow-on. Did you do a uniform mixed layer depth? Because back in the olden days, that's what we did.
In this case, I haven't done uniform.
It might, like if you do a uniform deep layer, it
Or
might be.
just look at the mixed layer depth. I have a sneaky suspicion it's really shallow around South America or something, and you're getting a runaway feedback that propagates because the ocean, there's no heat capacity in the ocean.
Yeah. No, it's a good, yeah.
It gets cold, it gets cloudier, and then that spreads.
Let's hear Dan's question.
Yeah, I'm just curious what happened in that model where it did crater. Did it become a snowball planet? Where did the energy go? I mean, I know that this doesn't balance energies, but is there a way to correct the tendencies so that it balances in a global mean albedo sense, or for?
Yeah.
I mean, did the albedo just go through the roof, and so you're reflecting all the energy away from the planet? I mean, what happened?
And the sea ice will start to grow.
Oh, it does grow?
Yeah.
Okay. Clouds first it starts probably with the clouds thickening as it cools.
Yeah. I mean, so this was a runaway snowball condition. Is that what happened, or is it just that it? Like what actually happened in that state?
Yeah, I don't know.
I mean, it's pretty clear that up to 40 degrees south, at least, sea ice was forming, right?
Yes, but
yeah.
Presumably it's not matching its equilibrium climate temperature anymore. If you were to calculate the albedo and calculate I guess you have to factor in some kind of greenhouse gas effect because of the atmosphere, CO2. I don't know. Yeah.
It's reached like a new equilibrium, right?
Crazy, interesting, but I mean, I think this is really cool to echo what was said before. I think that my students are also probably one of the emails you're getting that are saying we want to run a slab ocean model, and I know a lot of people in the exoplanet are just actually setting Q flux to 0. They're just saying it's 0. So when they're running SOM.
Yeah. But I feel, I was really surprised that it was as dramatic as this. I didn't expect this. I was thinking, we want to have it's important when you want to have accurate climate sensitivity that you will reproduce the surface temperature of the climate model within
Well, the good news, the sensitivity of that red one's probably not very high.
Yeah.
It's probably a lot lower.
Yeah, no, I got a sensitivity with the rate of 60 Kelvin. The highest sensitivity. No.
Oh, it's 60. Oh, because the other, the 2 times CO2
The
doesn't.
2 times CO2 doesn't.
Doesn't.
Okay.
Can I just say,
But-
it just doesn't seem that surprising to me that this thing is nosediving into a cold climate. I mean, the differential equation you put up is a balance between two terms. And if you look at the Q term, to me, if I'm looking at it, red is systematically lower than blue. The Q flux is systematically lower than blue. And so it just seems to me that it's.
No, that's not the Q flux.
No, because-
Oh, no, you're talking about the upper right.
Yeah, the upper right.
This here?
Yeah.
Sorry.
Red is systematically lower than blue.
Well, I don't know.
It's not in the southern hemisphere.
All the northern hemisphere pretty much is.
Yeah, but it craters in the southern hemisphere,
Never does it really go above.
right?
Blue.
Except where it's
If you
cratered.
look at the mean value of the Q flux,
That's where it's
and this
cratering,
is
My eyes aren't very good, isn't it above?
0.3 in CSM, minus 0.03 watt per meter square in CSM1 and 0.4 in CSM2, then this is not
enough to change 20
enough to
Kelvin
change the,
in 80
yeah.
years.
But like around the sea ice edge west of the Antarctic Peninsula, I feel like they are different, right?
Yeah.
And maybe that's just triggering some feedback.
Yes, yeah. Can I provide a historical reference here?
Yeah.
Again, back in the old days, we used to actually do these flux correction that Dan was talking about in the SOM model. So it could be something that if you want to pursue the idealized, you could do something like that as well.
Yeah.
Or with like uniform, mixed layer depth or something like that as well.
Yes, yeah. No, it's a good, yeah. And the whole reason of this method, it was to avoid to have to make any correction, and that's why they create this some version, but then after they compute a Q flux for every version of the model, and
I think there's been lots of creative ways to get a SOM working without having to run a fully coupled run, and that's one of them.
okay,
Yeah. I'm not saying it's right or not.
Yeah.
I'm just saying it's been used.
Yeah.
I guess if there are no more comments on Cecile's talk, I mean, we had scheduled some discussion, but I think it's too late to dive into a general discussion at this point. We're 7 minutes away from when we're supposed to adjourn anyway, so let's just adjourn early.